excited to have two very nice speakers here, Maria Schult and Juan Caraquea. Maria is working at a quantum computing startup, Xanadu, in Toronto, as well as for the University of KwaZulu-Natal in Durban, South Africa, where she also received a PhD in 2017. She is a co-author of the book Supervised Learning with Quantum Computers, and a lead developer in Penline software framework for quantum differential programming. We are very excited to have her here. Juan is full-time researcher at the Vector Institute of Artificial Intelligence, also based in Toronto, and he works on the intersection of condensed metaphysics, quantum computing, and machine learning. Before coming to the Vector Institute, he did a PhD in Italy and has a postdoc at George University, Penn State University, and worked also as research scientist at D-Wave Systems. So welcome, and yeah, hello.
Great, thank you so much, Asya. Yes, before we start with the first video, I just wanted to welcome you also on behalf of Juan and myself. And I wanted to talk a bit about what to expect and what you need to have as a background for this. The short answer is almost nothing, hopefully. And also thank the organizers for the opportunity. I know everyone always does that, but for us, this is very special because quantum machine learning, and you will learn this also like over the next hours, is a field that has exploded in quantum computing research and which is run by physicists. And it's still quite novel in machine learning. So there are different types of machine learning scientists you get. Some of them have maybe a physics background and they're always very curious, and some of them want to actually like come to the dark side and start building a field in machine learning from scratch. So this is really exciting for them. But the majority of machine learning researchers are, like just looking out for quantum machine learning if they even know about it, and are wondering what's actually this all about. And this is rightfully so, because quantum machine learning is still a research area that has to develop a language that is interdisciplinary accessible. So a lot of it is still published in the language of quantum mechanics rather than machine learning, which is also changing slowly. But secondly, quantum machine learning is a field which you will also see that reasons about computers, where the first prototypes are here, but the computers themselves are not here. So one of the main tools of machine learning, which is benchmarking, is not accessible to us. So a lot of the things we're trying to find out at the moment, we have to find theoretical channels that go through machine learning, but also go through quantum computing, which is really a major feat. So this is why it's still a very active beginning research area. We hope that this tutorial does two things. So first, we want to show you kind of in general how people approach this topic, and basically also like talk a lot about the limitations of what we can do at this stage. And then we want to share a lot of aspects of why we're actually very excited. So especially in the second part, you hear, like connections between physics and machine learning, or quantum computing and machine learning, in terms of kernel methods, in terms of parameterizing quantum states. And so these are the exciting connections that we want to present here as examples. Yeah, and lastly, what technical requirements do you need to have? So you do not need any background in physics or quantum physics. We won't give you a big introduction into this field either. This would be a completely different task. We want to just give you enough to, pinpoint those ideas and get a little bit of an intuition. So don't expect that afterwards you understand exactly what quantum physics is and what quantum computing is, but you will know quite a lot about it, hopefully. So then quickly, like looking at the schedule and what you need for the different sections. So the first section will be like very general, so everyone should be able to follow this very easily. The second one will introduce quantum computing a little bit. What is of advantage here is to know some linear algebra and to know the idea of probability theory and sampling on the most like practical level. Then we go into a little coding example. If you know Python, I guess most of you will know this. You'll be find it very easy to follow. And then we go a bit into a more theoretical part. That's the fourth video, which will talk about kernel methods. So this will be of advantage, but also not needed. And then the last part, Juan will talk about connections between machine learning and many-body quantum physics, where maybe physicists will enjoy like a lot of the material, but again, you don't have to be a physicist. Okay, that's it for me. Juan, I don't know if you also want to say hello quickly before we start.
Hello, everyone, and thank you for tuning in, and thank you to the organizers for giving us the opportunity to give this tutorial. And welcome.
Wonderful. Wonderful. Okay, cool. We can start the first video then now and see you in the chat. Welcome to the NeurIPS 2021 tutorial, Machine Learning with Quantum Computers. So this is the introductory part 1, and we will tackle the elephant in the room directly. So most of you might be here because you have got the question, can quantum computers help with machine learning? Should I know about this to be, like relevant in the future? And as in every research discipline, a question of this size is impossible to answer. But in this case, it's actually even harder. I want to show you why this question is really, really hard to tackle with the tools that we have at the moment in quantum computing. On the other hand, I also want to show you that this is a super exciting intersection that, has a lot of future potential, because there are lots of elegant mathematical connections that plugs quantum computing directly into machine learning ideas and machine learning paradigms. The learning goals here are basically also to understand more the human context and the research context of quantum machine learning and why we ask the questions the way we ask them, why we write papers the way we write them, and also to be able to locate what we will do in this tutorial into, this really diverse emerging landscape. And since we only get to like a bit more of a look into quantum computing in the next section, so here's some working definitions. Everything you need to know. Quantum mechanics. My family sometimes asks me if I'm doing something about rockets or gravity, but quantum mechanics is actually the opposite. It's a physical theory about the small things, about photons, about atoms, and it tells us about measurement results or the probability of measuring something about these systems. And it was fully formulated around 100 years ago, so it's probably as old as machine learning itself. Quantum computing means to use these laws of physics to build information processing devices. So what happens if quantum computers are based on the behavior of atoms or photons? And it started like around 30 years ago, so it's also quite a mature area. And what we talk about here is quantum machine learning. It's quite new, it only started a couple of years ago, like in earnest. And it means to use these quantum computers to solve machine learning problems. And so to understand how people have, approached this idea of finding an intersection of quantum computing and machine learning, you have to understand what tools we actually have in quantum computing so far. And for this, you have to understand that quantum computing is as a big transition of a research field that has been, theoretical, and this theoretical part is called fault-tolerant quantum computing for 30 years. The textbook of Nielsen and Chong, I can really recommend. I think it's one of the most cited textbooks in physics of all times, and it contains almost everything you need to know for the first 10 years of your career. But so this theory has recently been turned into like practical applications when the real first prototypes became available. And you can imagine that this really changes the questions people ask and what they deem worthy of publication. And so there's a real like rethinking of the way we approach quantum computing for the longest time. And it starts becoming a bit uncomfortable because now we have to really see what happens on the ground. To go a little bit deeper into these two paradigms, or to describe them a little bit better, because this is also important for quantum machine learning to understand where this comes from. So the fault-tolerant approach, so the basic assumption is that the basic unit of computation, which are qubits, that you have them in abundance. So for example, millions is very easy to come up with. And you need this abundance because of error correction. So as you know, like computers are physical hardware, and physical hardware makes errors, and errors have to be corrected so that you can be sure that your result is precise. And this turns out to be really hard at quantum computers. And by hard, I don't mean like that there's a problem there. So we know that it's doable, we know that it scales well, but there's a lot of basically physical subsystems or systems you need to create one logical system. So that means you know that there's a little bit of an overhead that we need to implement algorithms in an error-corrected way. And so this is why you need an abundance of qubits as well. And then the use of these fault-tolerant quantum computing ideas, well, there have been lots of proposals of algorithms. You might have heard of Shor's algorithm for prime factorization. Grover search is an unstructured search algorithm. And then a more recent one was HHL algorithm for matrix inversion. But what's important, these algorithms have been developed and studied under a very, very specific lens. And this lens is always computational complexity. So that's the idea of how does the scaling of your algorithm, or how does your algorithm scale with the size of the input? And then lastly, like, these, when fault-tolerant quantum computers that are error-corrected are available is not entirely clear. People always say 5 years, 10 years. There will probably be a gradual, introduction of those, but they're definitely not here today. And just to give you a flavor of this, I kind of like just copy and pasted a bit of a result, from a typical and very nice paper of fault-tolerant quantum computer here from Lo and Chuang. And so you always see like there's some kind of input specified. There's often like some talk about Hamiltonians or unitaries or some physical objects from quantum theory. And then in the end, people introduce upper bounds on the scaling that kind of depends on these inputs or some norms of these operators that we introduce here. And then follow-up papers always try to like lower the bounds, lower the bounds, lower the bounds. So getting back to these paradigms, we also have then near-term quantum computing, which is this new way of this rather fresh way of approaching the same problem. And in near-term quantum computing, so inspired by the hardware that we have, we always think about like a very, very strict limitation to the number of qubits. So from 10 to maybe hundreds or thousands. And in this scaling, we cannot actually correct any errors. So we can sometimes mitigate them, but in the end, the longer your algorithm, the wronger the result in the end. So we have to really be very stingy on the size of the algorithm as well. And so there was a new paradigm or new design that's also important for quantum machine learning that came up in this near-term approach. And this was is called variation circuits. And the idea is basically, if I don't know how to design a really small algorithm, because it's really hard, you basically just parameterize your circuit, you define a cost function, and then you optimize the parameters to solve the goal of this algorithm. And obviously this immediately reminds you of machine learning because, like a lot of machine learning uses basically optimization in this sense. And so the whole paradigm of this is like run it and see now on your devices. And just to give you a feel of like what you actually run this on. So there are different like setups. So you can, by now there are, I don't know, 50, hundreds of quantum computing libraries. You can just pip install most of them. So a lot of the frameworks are in Python, but not all of them. And then you can run your quantum algorithms on simulators that are installed on your local computer. When things get a bit bigger, you need remote simulators. You need some big clusters to run this stuff. And so, like you just like send your programs to a remote backend. And then obviously you can also run them on real devices that are also available as remote backends. And in lots of the languages, you literally can just like change whether you run it locally or remotely on actually real hardware remotely. You can change this only with a few lines. And why this is interesting or important is that quantum computer these days is not only the design of these algorithms in the end or these chips, but by now we actually have to design the entire pipeline. So a lot of like, setting up clouds, worrying about latencies and things like that are actually part of quantum computing these days. Okay, so to summarize this idea, so what tools do we have? Or the important part here is that if you think of all quantum algorithms that we can run on these quantum computers that are coming up at the moment, basically out of necessity, we have two areas that we have focused on that we actually know something about, and they are rather small as usual in research. The one is those quantum algorithms we know the computational complexity of, so they have to be problems that are very structured, that we can, that are really like working for our theoretical tools. And it's also important to say that there are often bias towards algorithms where we know that the classical equivalent also has a certain like complexity structure. So if we can't say anything about the classical algorithm, it's often useless to claim some quantum advantage, then we don't even look at it. And the other little area is these like very, very short, very small, often variational quantum circuits. Okay, now how to make machine learning quantum. And so this is the next little bit that we need to understand a little bit more the question of quantum advantages for machine learning. And for this, I want to look very briefly at a supervised learning task that's absolutely standard formulation. So you've got a probability distribution over inputs and outputs. You've got some finite sample set of those. You've got a loss that compares labels and can tell you how good predictions are. And now the task is to find a model from a class that you have predefined, for example, a model class of neural networks or SVMs that minimizes the expected loss over the data distribution. So in the end, we want to know how good is the model on all data I could expect to see. And obviously, as you all know, this is inaccessible to us, mostly because this data distribution is some abstract concept that we don't really have in real life. So we do empirical risk minimization. Instead of solving the original problem, we solve a problem where we minimize over like the finite sample set. And then we hope for the best. We hope that the problem solves the original problem. And so in the early days of quantum machine learning, so starting like maybe 2012, there were some exceptions as well, but like the first approach was to do what quantum computing always does. And this is you take something that normal computer scientists have figured out, an algorithm, and then you just see if you can speed up the scaling. So how this would work in machine learning, you solve your machine learning problem, but every time, for example, the model is evaluated or the optimization makes a step, you would outsource the algorithm to a quantum computer. It will return the same result as the classical computer, but it hopefully does that faster. And so what's important here is that your implementation changes, but your problem doesn't change. And now you could call it in a second wave, or very recently in quantum machine learning, people have started to like go a little bit deeper. And so what they do is to change something really in the problem and make it quantum. I'm not saying this is only happened in the last couple of years. So there were very early quantum machine learning papers where people really like started with the problem as such, and they asked, what is the data distribution as sampled from a quantum experiment, or things like that. But so a real explosion has happened only in the last couple of years. And the most popular approach that we will look into here as well is that you just replace your model class with quantum circuits. So you say, if I say my models are not neural networks, but they are computations from a quantum computer, what actually happens? And the important bit here is you can see that the problem as such changes. So you have to start answering questions like, how good is this actually? How well is this generalizing? Does this actually do something like deep learning? Do we get interpolating classifiers or not? You can also ask like, how close are these models to neural networks? By the way, the answer is probably not at all, but we call these models sometimes quantum neural networks to get a piece of the commercial cake, I guess. But so a lot of like interesting questions happen that are very hard to study, as you can imagine. And finally, we can like ask this question like about why quantum advantages are actually so hard to find, as a kind of like announced right at the beginning. So let's say like this here's the setup. So we have to show that quantum algorithms solve a learning problem well, while no classical algorithm can achieve a similar performance. So this is a very typical quantum advantage, way to phrase quantum advantage. And now the first problem is that in classical machine learning, this is usually done by benchmarks, right? You just like run a model against another one, and then you compare basically the runtime and the performance. And this is something we can't do because we only have these very small devices. And I can assure you that nothing of relevance, nothing much bigger than an iris data set can actually like enter a quantum computer without fundamentally downsampling the data set or reducing it or doing some other tricks. So the real devices are kind of out of the question here. So now that means that show means actually to prove. So we have to prove that a quantum algorithm solves a machine learning problem well, and that a classical algorithm cannot do the similar thing. And if you have ever tried to show that an algorithm, even in classical machine learning, does well on a learning problem, this is an extremely hard task. I mean, try to find literature on neural networks being better than kernel methods or the other way around. So there are a lot of little hints you can always like put together, but it's a very, very hard question. And we don't only have to solve this question, we have to also show that no other algorithm could actually achieve a similar performance. So you almost have to like search over the space of algorithms and say something about this. And the last bit of difficulty comes on top of this is that deep learning doesn't only give us really, really high baselines. So the way the algorithms are performing at the moment in classical machine learning is really, really good. But also obviously like little access for our theoretical tools to enter there. So like if you don't have a good theory about learning in deep learning, then how can you like have a theory about quantum effects on deep learning? And so the way people approach this a lot, and you will see this often in papers, so some papers just like run algorithms, benchmark these small ones. A lot of them actually do that and then just see what happens. But the ones that actually really tackle the question of quantum advantages on a larger scale, they always have the same strategy. They take a problem that quantum computers can provably solve better, so something that we know for 30 years already, and then they change it into a machine learning task, for example, to propose a distribution of data that we want to learn, or to propose a hypothesis class that we want to learn from. And so obviously your problem now becomes like a very abstract, a very biased. So in this last paper in the references, you see that, like it becomes like a model that has a huge inductive bias towards quantum computing. By the way, I forgot to mention the paper references down here are always archive reference. So physicists put everything on the archive, so you'll find things there, and it's all free. Okay, so back to this problem. So now this is like what you can do. It's an academically wonderful feat to basically show from front to back that a learning problem is solved on a quantum computer better than on any classical computer. And there have been like a few voices like recently, and I have to disclose that I'm a very strong proponent of this argument, that maybe we're doing the wrong thing here. So maybe the question why you're all here, maybe, can quantum computers be better, is at this stage not the right question to ask. One of the reasons is that these very pathological, very abstract problems we are kind of at the moment being able to solve. So these big limitations of the question might not actually tell us anything about applicability and what people call real life tasks that we're actually interested in. But the second one, that's probably a bigger problem, because I mean, doing abstract research, there's nothing wrong with that, is that as most of us are physicists, and as physicists, you want to understand. You don't only want to like prove this is better than this, like we're not marketing experts or something like that. We want to actually understand mechanisms. We want to understand what quantum theory induces in a learning problem. And if you basically put all your energy into constructing these problems very artificially, you might not be able to actually like draw so many conclusions about like a real understanding of toy problems that we can analyze. And so in these last couple of minutes, I want to convince you that, or I want to show you that despite it being so hard to answer the question about quantum advantages, and maybe you also like, papers are technical and you might not get very satisfying answers to this question, there are a lot of absolutely beautiful connections between quantum computing and machine learning that might, in the next years, like give you a big breeding ground to ask this question better, to reformulate it into something that you can handle. And so sorry about the memes. I'm not very good at memes, and I don't know much about boxing or mangas or anything, but I thought this like actually really shows this nicely. There are a couple of fruitful connections. We are and we will stay here in this realm of interpreting quantum algorithms as machine learning models. As I said, this is one of the dominant approaches. So this is not just a choice of topic, biased by my expertise. Although I might bias it a little bit to supervised learning problems, which are sometimes a bit easier to handle. So this is already a really nice connection. You will see that quantum computers are very genuinely models, machine learning models. You can parameterize them super easily. They are very easily understood also as generative models, because quantum computers, as we will see, are samplers in some sense. The second connection is that quantum computers can literally be plugged into modern deep learning pipelines. So we have figured out how to compute gradients of quantum computations. So you can now just extend your PyTorch, your JAX, your TensorFlow framework by quantum gradients. And you can, for example, train a big deep neural network, having a little layer or a little computation being quantum, send it to the quantum computer, and your gradient computation framework knows how to like ask your quantum computers for gradients. So in short, you can literally do hybrid quantum classical machine learning already since a few years rather easily. So this was really a big, a big step in quantum machine learning. So more on the theory side, and this is like a topic that I'm also really very much involved in, we have also a very important connection. We know now that mapping data into quantum states or into your quantum computer can be interpreted very well as a feature map, because measurements kind of do something that you can interpret as linear decision boundaries in like some kind of feature space in this quantum Hilbert space of some sort. And so that means, in short, that a lot of quantum models that we study are actually kernel methods. And I don't need to explain to you why this is important. Kernel methods have not only been like a very successful like paradigm of machine learning, but also nowadays they're used to analyze deep learning. And so, for example, if you have Fourier feature models, or you've got neural tangent kernels, so they're really a tool of choice at the moment to say something about what's going on in modern machine learning. And if we can plug quantum theory into this, we can immediately inject it into these deep learning theories that are built at the moment. And then lastly, and this is Juan's field of expertise, so he will like take us on that journey. The connection also goes the other way around. So quantum states are, in some sense, like a way to describe something that's very complex. And this has kept people, busy for the last 100 years. And it turns out that neural networks are actually quite good at explaining or at describing these quantum correlations in a very compact description. So we also see that neural networks turn out to be a very useful representation of quantum states. And so the connection really goes both ways. Great. Okay, let's recap the introduction. I hope you learned by now that we have kind of two types of tools in quantum computing, these like very small simulations and 30 years worth of quantum computational complexity theory that is quite sharpened as a tool. Then there are lots of ways to make machine learning quantum, but there are these two big schools, you could say, where you just outsource like parts to a quantum computer, where often the machine learning problem as such is not so important here. So you can do this also without knowing much about machine learning. You just say, oh, machine learning uses matrix inversion. We can run matrix inversion on a quantum computer. But recently, there's actually an approach to quantum machine learning that changes the learning problem fundamentally. And this is this idea of using quantum computations as a model class, or maybe even as a class of distributions that data is sampled from. And now I hope that you understand in one more iteration why quantum advantages for machine learning are really hard to reason about. This is an extremely difficult problem, even if you don't look into quantum computing to solve from a theoretical perspective. And lastly, I hope we can uncover, and this is what happens also in the remainder of this tutorial very much, we can uncover a lot of these beautiful connections between quantum computing and machine learning. Hello, we're back live here. I hope you enjoyed the first video, and we already saw a couple of questions to which we'll come just now in a proper Q&A. However, so for the first 3 Q&As, we want to actually give you a little task during the Q&A, which you can do. So if you need a break, you can also obviously walk away, get a coffee. If you want to hear the questions answered, then just stay on. But if you want to do something else, then maybe you can use this break to Google everything you can find about quantum machine learning. So for example, the first thing you might find is the Wikipedia page, which is absolutely shocking. It's in a very, very bad state because I think most of it was written like a couple of years back on a conference at night where everyone had beer and we just like made things up in different groups. So you'll find like a lot of content with different like levels of quality. Have a look, come back to us. If you have questions, if you find something interesting, post it in the chat. Let's just like all collect a little bit of information. Yes, and other than that, I'm handing over to the chairs for the Q&A, which will run parallel.
So, hello everyone. I'm Aram, along with Asya, one of the co-chairs. So, I think we have a number of questions in the chat. So, do you want to take some of these questions, Maria? And now is that it?
Maybe I can just, feel free to pick the ones that interest you, but maybe I can just answer a couple of the more logistic ones, especially the ones, sorry, about the archive references. So, so what you do if you need, so in the talks, you often see just numbers. And if you just Google these numbers with archive in front, so ARXIV, you usually find the paper on First Tips, so that's the way to get those. And the second one that I wanted to quickly just post a couple of links to is so quantum computing frameworks or software. So it's a bit like in machine learning, you pick your favorite company and then the software framework goes with it. There are a lot of packages from like back in the day that were coded up by academic groups and institutions. They're usually less well maintained as it goes because a lot of money, and time needs to be put into this type of thing. So let me just post a few and comment on them. So we've got, as someone already mentioned, Qiskit, which is run by IBM. I think it's really the biggest community around this software, so this is not a bad place to start. Google has developed Circ, which is a bit more specific. I think Amazon came a bit later, or AWS Amazon came a bit later into the game. They've got a framework Bracket, which is especially like used to like run workloads on like remote backends that are highly parallelized. So there's a whole basically a whole pipeline you can build there as you are kind of used to. I just want to post like one package that I really, really like, which is called QLAX. I think this is not developed by a company, but it's unbelievably fast. So I find this quite interesting. And then I'll post 3 links in the chat that are quantum machine learning packages. So packages or software that's written with quantum machine learning, with optimization and things like that in mind. The first one we see later an example of, which is something that the company I'm working for is developing. And then Google has, for example, their own extension to TensorFlow, which is called TensorFlow Quantum. I don't know if any of you knew. And there's a very beautiful package based on Julia, which is called Yao. So this is just a biased selection of this. Great, Aaron, I don't know if you want to pick anything.
Great. Yeah, I also put in one of the archive links I put in. There are a lot of, some of the questions are very open-ended, and hopefully we'll have time for a good discussion of them. Maybe we should start with some of the quicker to address questions, like talk about the gradients in these variational algorithms, and how do they compare with the gradients in a traditional neural network.
Cool. So this is quickly to address, it's just an absolute misnomer. The quantum research community always puts, or quantum computing community puts quantum in front of everything, and then you have no clue, is this run on a quantum computer? Does this have to do with quantum theory or mathematics? What is actually quantum about this? Sometimes it's also just some classical method to do something in quantum mechanics. So it's actually like a real misnomer. But what I mean here by quantum gradients is just gradients of functions computed on a quantum computer. So even if you don't know how to simulate the function classically on a classical computer, there are still methods to get gradients out of them. But the gradients are exactly what you know. They're just like, vectors of partial derivatives of parameters with respect to outputs of functions. And these functions are computed on a quantum computer.
And I guess how you get how you learn the gradient might be different, but the definition is correct. There are. Well, I guess another question, I don't know if you want to speak to it now or later, is anything about the connections between neural nets and variational quantum algorithms.
Yes, so we get into this a little bit later. Often people in quantum machine learning research call variational algorithms, so these variational quantum computations, they just call them quantum neural networks. Mathematically, you will see that they look completely different. They're basically just in some sense, you can think of them as this linear algebra or linear transformation of something. So like the idea of nonlinearities in a neural network and quantum theory is not very easy to unite, although there were thousands and thousands of, people who have tried this. So I think this one we see a little bit later on. This will be easier to answer, when we've looked into the variation circuit with some coverage.
So yeah, I think for a lot of these we'll get into more depth later in the session, right? Oh yeah, there's so many good questions. Maybe one question was about you posted a bunch of links to libraries, and this tutorial is about getting started. One question is about what can a non-expert do with these libraries, and maybe I would twist that a little bit to say, what should a non-expert be reading along with these libraries, as they encounter things that they're unfamiliar with.
So there's millions of levels in which you can go into quantum machine learning, exactly like it is with normal machine learning as well. If you're just an enthusiast who wants to have a look, then if you go into these libraries, you just look at the documentations. Usually they have fantastic demonstrations and tutorials because, those companies want you to use their stuff. So they're interested in like everyone, having an easy start with it. And then very often they have examples where you play around with qubits. In the quantum machine learning libraries, you train little qubits to do some simple things. And you often find also like, deeper dives into research topics that are very common. So I think for an enthusiast, this is enough to do. And then if you want to enter the research, you will quickly find, as I mentioned, that there's a lot of jargon that's used. So it might be at the beginning a little bit difficult, but people get more and more open to, kind of adapting their jargon to machine learning. So it gets more and more familiar if we go into the papers. But in the papers, if you scan a paper, if you open a paper and you just scan it, you will immediately kind of see if this is like super quantum computing research, where almost nothing, it's complexity proofs that use methods that people have figured out there in like during many, many years, in which case it's really good to go and first study maybe some basics of quantum computing. But then there are also lots of papers that really just play around, that think about generalization errors, that prove generalization bounds for quantum models, where you might find it a little bit easier. So in some sense, at the moment, it's just a matter of, opening the paper, get your intuition and see if it matches you. And if not, maybe go back to the software and code yourself and get the knowledge from there.
Great. Yeah. And I'm not supposed to be answering the questions, but I'll just briefly say that quantum computing is easier than quantum physics, in my opinion. So, you should, if you're a newcomer, try to learn quantum computing and someday learn physics, quantum physics. It's beautiful, but definitely don't need to do that for quite a long time. There were a few questions. Go ahead.
There's a lovely quote by one of our colleagues, like Scott Aronson, who says somewhere, I had to go through all the history of physics and understand everything about optics and this and that, only to understand that quantum computing is just complex probabilities. I mean, which is a bit shortened, but that summarizes it maybe. Yeah,
makes it sound easy. So a few upvoted questions were about can we use quantum machine learning for big data problems? Also another question is what are some hybrid machine learning things that have done that have good demonstrations of hybrid quantum machine learning? Both are quite open-ended, I think.
So I mean, in some sense, so if you look at what we look into these variation circuits, how they've been put into classical machine learning pipelines, this is very often, or this is usually a method that is very hybrid. So what you do, for example, you could take a neural network, you could take a layer out, and you just put a quantum computation in. And this is a very typical example of a hybrid system. There are a lot of more dedicated studies to show how this hybridness can actually, how quantum and classical systems can interplay. But in general, a lot what we do is hybrid anyways at this stage. The first question, I should have noted it down. Aaron, give me
big data.
Oh yeah, the big data. So the big data was, in my view, but I'm a little bit biased there, I think in early days of quantum machine learning, this was always a bit of a advertisement campaign to say quantum computers are so massively parallel and they are so fast, maybe we can just load in big data and then, we can process it faster. And a lot of the early algorithms were also interesting methods of how to do something, something like matrix inversion really, really fast. So to do convex optimization or things like that. And maybe there's a bit of leftover from this, but I think by now people have experimented a lot with these very small quantum computers and they realize encoding data actually doesn't come out of thin air. So every data you have to encode it into a quantum computer. So there's a big first step of what to do with this big data, and how to do it is also not entirely clear. What's good representations of this data in terms of quantum state? So I think if someone says quantum computers are good at big data processing, that is very, very, hard to argue with the evidence that we have at this stage. It could be one day, but we don't know yet. Yes, and maybe if I can, I also saw a question about quantum advantage. Aaron, do you mind if I quickly also comment on this? Because
go ahead,
so what else are advantages? Yeah, I know we only have a couple of minutes left, but so I think this is a really important one. So the typical thing that quantum computing scientists always look at is speed. So they want to speed up algorithms. And this is why this idea of, take something from the pipeline, just speed it up on the quantum computer. And obviously, people slowly started realizing, machine learning is not all about speed. I mean, it has to be fast, but also it's about accuracy, generalization error. So there are a lot of studies about that now. I personally start really thinking about quantum advantages in a much more wide sense. So for example, think of sample complexity. You put an inductive bias into your model that matches your data set. Maybe the data is from quantum physics or from physics. Maybe you can learn from pure data. But maybe you have an energy efficiency. Maybe you can implement a neural network in a quantum computer run on optics, and the non-reversibility of quantum theory guarantees you something in terms of energy. That's long in the future. But then the last one, which is a quantum advantage, maybe there is a level of understanding we can bring into these models and how they meet biases in our data that really works. So this is basically the highest level of a quantum advantage. So I think we can open this a lot more to what people have analyzed in the past, and this is probably happening at the moment as well.
Great. So I think we've about a minute left or so. And I don't know, do you want to do it? And the remaining questions are getting bigger.
So, what we do is maybe we just collect a couple of the questions. If we can readdress them in following Q&As, we kind of flag them. And the other ones I try to answer in the next session so that, no one's goes unanswered.
Sounds good. And everyone, thanks for the great questions and keep upvoting them also. That also is, it's good to know what people are interested in.
Cool. We can play the next video then. Thanks.
Yeah.
So welcome to the second part of the NeurIPS 2021 tutorial on machine learning with quantum computers. In the second part, you'll meet the main actor of this tutorial, which is the quantum computer itself. So we want to give you a bit of an idea of what we mean when we talk about quantum computers and help you to kind of like see what is actually different to when you talk about classical computers. And if you've ever seen an introduction to quantum computing, you often see that people start with these things called qubits, then they give you some Dirac notation that you have never seen before, and then often they kind of expect you to really understand already all the equations in Dirac notation. And we want to do it a bit different. We assume that most of the audience here is proficient in the idea of machine learning that has something to do with probability theory and sampling. So the idea that you draw samples from a distribution. And this is in some sense all you need to know to understand this section. So our learning goals are kind of to grasp this idea of a basic working principle of a sampler, a computer as a sampler, and then to get a bit of a first feeling, although we can't go super deep here, of what is actually special about sampling from a computer that's based on quantum mechanics. And then thirdly, we want to also introduce you a little bit into the maths of how to actually compute things you're interested in terms of your samples. For example, what the probability is to see a certain bit string or not. Okay, let's go right in. So when we say that quantum computers are kind of special kind of samplers, this is what we mean. So think of a classical computer as just a map from bit strings to other bit strings, and these maps are usually facilitated by circuits, and these circuits on a very elementary level are represented by logical operations that act on bits, so some kind of information processing that acts locally on bits. A quantum computer has a very, very different working principle, and this is not due to the fact that it's quantum, but it's due to the fact that quantum mechanics is a probabilistic theory. So we have to think of these computations always as something probabilistic. So in a quantum computer, you could imagine you take an input, which is a bit string, and we'll see that especially in these near-term quantum computations, you might not even have a bit string. You could also use some kind of continuous, like a hybrid analog digital system, so you could use continuous inputs. But for now, in the traditional, most simple case, we just consider a bit string. And then you also apply some kind of circuits, and we'll see that these circuits are very similar in the sense that we can divide them into small logical operations of some sort. But then the output is very different, because the output is not a deterministic value, but the output will be like a set of samples of bit strings. Every time I run my quantum algorithm, I get a different sample in general. And so obviously some algorithms are supposed to be, stochastic in their sense, but very often, in normal computer science, maybe not machine learning. In machine learning, we have a lot of stochastic algorithms, but usually we want a deterministic result. And for this, we need to add a post-processing rule. So we've got a lot of samples that we get from a quantum computer. And in the end, we have kind of this implicit idea of, oh, let's, for example, define the result as actually the bit string sample that I see the most. Or you could also define an output that's continuous valued. You could say, let's just use the average value of my first bit or something like that. And so this is now the important thing. So this probabilistic way of running quantum computers is not necessarily what's different, because you know very well that we can run classical computers in a probabilistic fashion. So we can also run them as what I will start calling stochastic algorithms or stochastic systems. And one of the best examples is something like a generative model. So for example, a GAN, where I inject some kind of noise into a neural network, and then I run a neural network, and the neural network, every time I run it, the noise is different and it spits out a different output sample. Or in more general, you could just think of an algorithm that just depends on a number drawn from a random number generator. And then you go and calculate algorithm A, or you follow algorithm A if the number is larger than a certain threshold, or you follow algorithm B else. And so you can already see that in some sense, this idea that we kind of do computations in parallel, or kind of in some probabilistic sense in parallel in really, really large spaces of possible computations. This is not what is really unique about quantum computing. So what is unique, and we hope to go a little bit closer to identify this for you, is obviously that the systems, so these bits, are represented by physical systems that follow quantum theory. And so we call these systems usually qubits. So something is different in kind of the way that the physical platform is behaving in some sense. And just as a side note, so most of you might know that these qubits, for us, they are just abstractions. So you can take any physical system that behaves in a way that's explained by quantum mechanics that has kind of like 2 levels, and then you can just take n of them, then you've got like your n qubit system. And these days, like the implementations are extremely wide ranged. So we don't really know yet what's the winning technology one day. So for example, you could think of something as a photon going through a semi-transparent beam splitter, and then depending on which path it takes, you encode a 0 or 1. Or you could say there's a flux of a magnetic field in some kind of electric system or something like that. So there are very, very many ideas. Okay, so let's get a bit of an idea of what this quantum is actually now induces into this thing that I call like a stochastic system or an algorithm, which is always like this idea of you run something and you get bit string samples. So first of all, let's look at the levels that you already know, and this, like relates to this idea of if we want to introduce quantum computing to people who know probability theory quite well, we can actually touch quite a lot on their intuition for this. So if you have a kind of stochastic system or stochastic algorithm, you have kind of like 2 levels that you can describe things. The one is the empirical level. This is what you observe actually if you get those samples. So these are the bit string samples themselves. And then you have a mathematical level that is usually described by some probability distribution. And this distribution in general is a function. But if we are in the world of observations that are bit strings, these are discrete. So it's a discrete probability distribution. And from now on, we'll always think of probabilities here as just vectors. So these distributions are just like entries in a vector. And there's some kind of like ordering. So the first entry of the vector corresponds to the probability of observing 0, 0, 0, and so on and so forth. And now you can use this kind of like description on the mathematical level to compute exact values for some statistical property that you are expecting to see. But you can obviously, if you don't have access to this probability distribution, you can use your samples and just like estimate the statistical property. We see a couple of examples what I mean by statistical property just now. So now it turns out if your computer, your stochastic algorithm or your stochastic system is quantum, you don't get away with only the probabilities and the description that we had so far. So you need something else, and this something else is a quantum state. And a quantum state is a strange term. I sometimes compare it to like the way that machine learning people like talk about models, because models in machine learning are something that has a lot of connotation, and it's really hard if you remember back to really grasp what this is. And so the same counts sometimes for a quantum state. But in some sense, it's just the quantum analogy to a discrete probability distribution in our case. And so also you've heard that there can be functions in general, so some wave functions. But if we're just interested in observations that are bit strings, then we do have also the same case that we have a discrete kind of like setup, and we can write this as a vector. And so somehow the vector is organized in the same way. So the first entry of this vector is somehow related to the observation of seeing a bit string 0, 0, 0. So it gives you some information. But this information is not a probability, it's something slightly different. And one of the ways to see that it has to be something slightly different is that these quantum states, the entries, are complex values. So they're not like real valued like probabilities, but something a little bit more crazy. And so the second thing that's kind of like slightly different about this description is the evolution of distributions. So what do I mean by an evolution of a distribution? The idea here, so from the probabilistic level that you know, you could think, for example, of a generative model that starts with some parameters, and it kind of, you can describe it by a probability distribution P0, and now it evolves and you end up so with different parameters, and then you have another probability distribution. Or you can think of like changing the algorithm or adding layers to the neural network. So whatever you do in your algorithm, you can kind of think of it as actually taking an initial distribution to another distribution. And so the same is true for the quantum state in some sense. So the quantum algorithm is in some sense just a transform from some initial quantum state to a final quantum state. And think of it as just like having a system somewhere in the lab and you shine some laser light onto it. Or you do some other like physical things with it. And in the end, you get like a final quantum state. And so also here, there's a difference. So if you, I don't know, have ever looked into probability theory, if you transform probability vectors into another, you can do this, or you can describe this by this is a linear map, and you can describe linear maps by matrices. And this matrix has certain properties. You call this like a stochastic matrix. And these properties basically just ensure that the map keeps probabilities intact. So it keeps the idea intact that probabilities add up to 1. So it allows us to really interpret what comes out of this map. And in the quantum case, our transforms do in some sense the same thing on some level. But what we need here to have this conservation of probabilities is a so-called unitary matrix. So this matrix has complex entries in general and just has a slightly different shape or slightly different characteristics. So now this kind of comparison between the probability level and the quantum level that I tried to put up here might already explain quite a few things to you. So, for example, we always say that it's really hard to simulate quantum systems because they live in these really high dimensional spaces. And obviously these vectors have 2 to the n entries, right? If I have an n bit string, then I have 2 to the n different bit strings. So to describe some kind of probabilistic information or stochastic information about my system, I need to specify in the quantum case 2 to the n complex numbers, in the classical case 2 to the n real numbers. So this difficulty of describing things is actually not something that's specific to quantum mechanics because, and you know this, so for example, if I come back to the example of a GAN, if your stochastic system is classical and you just have a GAN, it's actually also really hard to write down a probability distribution of this GAN. So you can write down an algorithm that spits out samples. So you can kind of, use a computer to produce samples. But actually, we often do not even know what this distribution is. And the same case is kind of in quantum physics. If you have a system like a computer that spits out nice samples, but sometimes, or what 100 years of quantum mechanics in some sense really try to do, is to get ways or situations in which we can really specify this vector and do maths with it in some sense. And just a little note, in the last part of this tutorial, we will hear from Juan how these connections between neural networks and quantum states, so how neural networks can describe quantum states. In some sense, this is exactly what I'm talking about here, because the idea here is that if we can't specify these huge states, but maybe we can get an algorithm that can spit out or can directly tell us something about the sampling behavior. So this is in some sense a connection to there. Okay, cool. Now I want to give you kind of 2 very simple examples of how you can use these descriptions to kind of get stochastic properties out of your system. So let's say, for example, you are interested in how likely it is to observe 0, 0, 0. So this is some question you could ask about your stochastic system. And obviously, if you have samples, so on the empirical level, what you do, you kind of construct some kind of estimator, and this approximates this number that you want to find out in some sense. So you could, for example, count the number of samples 0, 0, 0 and divide it by the number of total samples. And if you've got enough samples, we all know that you get closer and closer to an answer to this. On the level of probabilities, you'd also be, in this case, this is a very simple question to answer, because this is what a probability is, right? It describes, in some sense, this likeliness of observing a certain bit string in this case. So you just take the first of the probabilities, and this is exactly what you want. So now in the quantum sense, these computations always look a little bit more complicated, and they always have this very strange structure I was talking about at the beginning. So there's always the state involved and then some kind of matrix. And that matrix basically specifies in some sense what you want to get out of your quantum state. If you look very precisely about this kind of psi times a matrix times psi, and one of the psi's has this dagger. This means it's instead of a column vector, it's a row vector, and every entry is complex conjugated. So it's a complex conjugate transpose. So this is just a mathematical notation. So if you look very closely at what this thing does, in some sense, this matrix, if you multiply it with the vector on the right, it picks out the first element. And now if you multiply the row vector again with it, but it's now complex conjugated, what it actually does, so it's a very complicated way of just saying, take the first element of my quantum state vector and take the absolute square of it. And this equivalence is known as the Born rule, so that basically the entries of the quantum state in some setup, in some basis for some situations, you can just say, if you take the absolute square of them, then you get to probabilities. A little side note, so sometimes you might have heard of quantum algorithms always having quadratic speedups, and you can actually quite nicely sometimes link the square that comes into this translation somehow that you see in this equation to these quadratic speedups that you see. And the quadratic speedups are also the ones that are the best proven. You know, they don't have a lot of terms and conditions. We are pretty sure that quantum computers can speed up a lot of kind of very general applications quadratically. So that's quite an interesting like connection there. Okay, cool. So now you see like the quantum mechanics just make things a bit more complicated in how you're trying to do something that's actually very simple. I'll give you another example that's a little bit more, you know, like involved. So now maybe you want to ask like, how likely is it that the first bit is in zero? So you want to know something about a subsystem. And again, you could just like count your samples where the first bit is 0 and divide it by the number of samples, then you get like some kind of like estimation of this value. In the probability vector, if it's ordered in the way that bit strings are usually ordered, what you can do is actually just add the first half of your probability vector, because this is all the probabilities corresponding to bit strings where the first bit is 0. And now in the quantum formalism, maybe you already like catch up with this easily. You just have to change this matrix and you now answer a different question with your state. And so you, instead of having just like one entry being 1, you have to now have the first half of the diagonal being 1. And now what it does, it takes out the first half of your vector, and then the row vector like kind of like comes to it, and then this absolute square thing happens. And so you get actually exactly the same result than if you like look at the probabilities. And so now you might ask, and this already gets us basically to the core of it, you might ask now, okay, at the moment I've only done, you know, the same thing. So the quantum formulation gives me basically the same answers than the probabilistic formulation. It's just a lot more complicated. It uses a matrix instead of and 2 vectors and this complex conjugation instead of just like probabilities. So why do we need this? And it turns out that the situations we have been looking at now might not be so very interesting, but think of, for example, if you now have this matrix and you do not only use the diagonal. So if you use the diagonal, you will always get some linear combination of probabilities. But now if you have non-zero elements on the off diagonals, you do something that's very crazy. And especially, and I haven't told you, but this matrix has the condition it has to be Hermitian. So this is another like kind of like property of a matrix, which is not so important. This matrix is basically with real eigenvalues. But it's also a complex matrix in general in quantum theory. So now imagine you have complex values on the off diagonal, and then this computation, this vector matrix, vector multiplication, can do really fancy things, because these complex parts of your numbers, they can kind of like start doing something that we call interference. So they can kind of like cancel each other out, or there can be like negative signs. So a lot more complicated things can happen. So in some sense, this quantum formalism is a lot more, you know, powerful to describe stochastic or probabilistic systems, but it always contains the classical probabilistic theory. So it basically just enlarges it. Now here's a little kind of side note for the people who are a little bit more advanced. So when I say like in, you know, these systems, so the stochastic information that we want out of our systems, we can just like write things on the off diagonal, and then we have complicated measurements, and then things get interesting. Turns out actually in quantum computing, we only use very, very simple measurements. So you might have seen so-called Pauli Z measurements. So they're a matrix. It looks very similar to this one. The matrix has 1s on the first part of the diagonal and then -1s on the other one. And it basically just rescales the question we ask here from how likely is it that the first bit is in state 0 to, you know, like a value where the bits are scaled between -1 and 1. It's not so super important. But what I want to say is like quantum computers usually implement in real life very, very simple measurements only. And so how is this possible? So it turns out that you can have a very, very complicated measurement, or you can actually implement a very complicated algorithm and have a very simple measurement. So why I'm saying this is that in these measurements, you can actually always think of like the measurement being really, really simple, but your algorithm being very complicated. So I said this is a bit advanced. I'll just show you kind of the equation that explains what I mean. If you have this vector matrix vector product that I told you gives you the stochastic information out of your quantum formalism, you can actually take this matrix, since it's Hermitian, you can make an eigenvalue decomposition, and you get basically a left unitary matrix, a diagonal matrix sigma, and a right unitary matrix. And now you can just like, conceptually like pull this matrix into the state and interpret like U times psi as a matrix times vector multiplication. And now remember, what you get here is actually an evolution. So what we basically did here is we turned like a complicated measurement M into a simple measurement sigma, which is this diagonal measurement that kind of like you can also like interpret very easily like as just probabilities and adding them and combining them, plus a very complex evolution. So in all of this gives me now the possibility to describe to you a little bit more clearly in this picture that we are at the moment, under these circumstances that we are, because quantum mechanics is really big and they're often like more complicated cases. But in the case where we are, where we have quantum computers, we have simple measurements, we can now actually pinpoint quite clearly where quantumness or where the interesting effects come in. And they come in where the algorithm happens. So where an initial state, and the state is some kind of quantum equivalent of a probability distribution, gets slowly transformed into another quantum state. And then we kind of like use this to kind of like draw samples from some kind of system. So this evolution is really like what contains the quantum mechanics here. So lastly, and this is also a bit of a side note, I just wanted to like use now this formalism that we introduced to give you a kind of an idea of 3 important terms that you might have heard before. So if you have introductions to quantum mechanics, you always hear about superpositions, entanglement, interference. I hope you already get a little bit of a feeling now why it's actually quite tough to start with those, because there are a lot of subtleties in like how they emerge and what their idea is. But so I just want to give you a little bit of an intuition for those terms. Superposition is a property of the quantum state vector or quantum state. And it basically just means that more than one of the amplitudes is non-zero. So you immediately get a superposition in our picture that we just developed, if you have like more than one of the amplitudes being non-zero. And I put in faint gray like an example of a classical probability distribution. And the intuition of, or the classical equivalent of superposition is in some sense just uncertainty. So which means that you don't have a probability distribution that's a Dirac distribution, but like some proper distribution. Of course, we know that in the quantum case, some uncertainty doesn't really cut it. There's not just, so lots of experiments and theories have confirmed that it is not just uncertainty that's happening there. It's not just a lack of information, but something different is going on. We know how to describe it with the formalisms I just gave you. We're not entirely sure, like, really what the basic natural principle or ontology behind this is. Anyway, so furthermore, you have heard of entanglement, and you can say that in the quantum state, this is a property of basically which amplitudes are non-zero. And the classical equivalent to this is a correlation. So if you've got, for example, a 2-bit string system, and you have a probability of 50-50 to measure 0, 0, or 1, 1, whatever you measure, your first bit will always be perfectly correlated with your second bit. And so this is like kind of the equivalence here. And then interference, I already mentioned this kind of idea, is basically, or in the largest sense, is the idea that evolutions and quantum states have these complex valued entries. And when you do matrix vector multiplications, these complex valued entries can cancel each other out. They can do some stuff here. So in the example on the right, you see, for example, a Hadamard, a very famous like quantum gate, a Hadamard transform, acting on some kind of quantum state. And if you do the maths, you can see that this minus sign that's there highlighted in red actually cancels kind of subtracts the second from the first amplitude. And what you get as a result is a state where, like the first amplitude has all the density. And also this example is quite a beautiful one, because this Hadamard transform has the property that if you would now apply it on the result of this computation, you would again get a state with I call it now density, but where both amplitudes are non-zero. And in some sense, a Hadamard is an operation you applied, it all of a sudden produces a state of, we think of a classical equivalent of maximum uncertainty. You apply it again, it has a state of minimum uncertainty. And this is something that's very, very strange for classical probability distribution. So I find a Hadamard gate is the nicest way to really like get into the weirdness of quantum. Okay, so now we don't go deeper, but we do everything again. But we do it now on a level where I want to introduce a little bit more the idea of quantum algorithms. So what you see here is on the left upper corner, you see the usual graphical descriptions that we use to describe quantum algorithms. On the lower right, you see basically this idea, but now I use picture notation of these quantum states, and you will see matrix vector multiplication just by like squares being like combined to each other. And the goal of this exercise is just at the end, I want to basically convince you or give you an idea that quantum algorithms can prepare states that depend on data and parameters. So we want to go into a little bit this paradigm of variational circuits here as well. Okay, cool. So how does a quantum algorithm usually work? So we start with an initial state. This initial state, again, think of state always as a distribution. So it's basically a distribution where we have 100% probability to measure a sample 0, 0, 0. And so the quantum state that corresponds to this type of, like stochastic system is a quantum state where the first entry is non-zero and all the others are 0. Just a little kind of comment, I just use the convention that in the first entry, only the real part is 1. But I could also just, call this entry plus 1i or minus 1i or something, because it wouldn't have really a difference here at the moment, unless your algorithm like introduces something interesting. Okay, cool. So this is our initial state. And you see in this picture, we always like put so this is the first time you see this Dirac notation, just because the imagery always uses it. But basically every line corresponds to one subsystem. And so in your head, you can think of it as 1 bit. And these lines are very similar to the lines in the logical circuit diagrams from classical computing. So an algorithm, I told you, and you can see it on the bottom right, is kind of like a matrix multiplied with this initial vector. And this could be like, in some sense, the entire quantum algorithm could be just expressed by one matrix. And this is a very, very general picture. So everything a closed physical quantum system can do can be described in this way. Obviously, we cannot really like handle these huge 2 to the n dimensional matrices. And actually, even in physical systems, we do not really like apply something to the physics and then it just happens. But what we do, we split our algorithm into small gates. This is the same principle also as in classical logical circuits. And the meaning of this is only that it's much easier in the lab to implement basically interactions of 2 of these qubits instead of like 3 or more. So most algorithms will consist of gates that act on 1 of these subsystems, 2 or 3, but not more. And it was one of the big results of the 90s, the Suva-Kitaev theorem, it's known as, is that actually any quantum algorithm, any quantum evolution, anything a quantum system does, a closed quantum system, can be actually split up into these small gates and in some sense also efficiently, so you don't have like some crazy overheads. And now this is something you do not see in lots of textbook, maybe more and more. This is this principle of having variational gates. And so the thinking here is this: if you think of a gate, basically think again back to your atom or whatever, and you shine a laser pulse on it or something. A gate is actually artificially a static operation, because in some sense, if you have a laser light, you can usually tune it. You can tune the frequency, or you can make it stronger or weaker. So you have actually physical parameters that you fix to something to implement these gates. And now in recent quantum computing, in near-term quantum computing, people have noticed that, why don't we just use these parameters instead of kind of like setting them to stiff values or fixed values? We literally just like use them as free parameters. And so what you see here is not a quantum algorithm, but it's basically a family of quantum algorithms. And depending on how your parameters are fixed, you pick one of these algorithms. And this is obviously very similar to a machine learning model. So I hope you already your brain already starts working and answering the question of how we can now use quantum circuits as machine learning models, which is what we will look at later. So now about encoding information. And I mentioned before that back in the day, algorithms always like started with some kind of like routine that basically encoded a bit string into a quantum computer. But nowadays, like people often do it a bit differently, especially in this like second wave of quantum machine learning, people do this. So let me go back. If you have these free parameters, I could now say at the beginning of my algorithm, I associate these free parameters with inputs. So basically, if I have an image recognition task and I want to encode an input into my quantum computer, an image, let's say the first pixel has a value, a black and white value of 0.2. I could just associate this laser strength or something with this value 0.2, not thinking of units or something like that for now. And so I could use the first part of the algorithm, these 3 parameters, to encode inputs into my physical circuit. The second part of the algorithm, I could kind of keep with 3 parameters. Obviously, I could mix these 2 as well, but sometimes it's conceptually clearer, as we will see, to separate them. And so what I get in terms of my mathematical description is obviously that this kind of idea of like a quantum algorithm that depends on, for example, X, so I call it here S of X for state preparation or something, actually gives you a quantum state that depends on X. And if you had, a lot of work in kernel methods or like feature maps, you already get your very important hint about something like we will get into back later that I already mentioned. And this is this idea that kind of quantum circuits of this kind can be understood as encoding inputs into high-dimensional spaces. Anyway, so this at the side, but then the second algorithm is just another matrix that you multiply with your vector, state vector, and this is trainable or depends on 3 parameters. So now let's go zoom out again and go back to like we just have any quantum circuit. Let's just like fill up this picture now with measurements. So in the circuit diagrams, measurements are usually these like boxes with this measurement device in there. And then you need to know, so especially when you work with software, so usually this idea of sampling 1 bit string from your quantum computer, which means to implement this very simple measurement that people call the Pauli-Z measurement, which is like a very standard simple measurement we use everywhere in quantum computing and quantum machine learning. So basically implementing this measurement, what you get out of this quantum computation is like a bit string, and we call one of these samples a shot. So if you ever heard of like I run my quantum computer with 10,000 shots, it means I get 10,000 bit strings out of it. And obviously I can use these bit strings to compute my statistical property that I'm interested in. And so as I said before, like sometimes you're actually interested in algorithms that whose results is not these bit string samples, but you want actually like a result that's a deterministic value or some kind of like number or some kind of like fixed number. And so we had this before. So this idea here of like, taking a statistical property or like something that I post-process and I use this as the output of my algorithm. And here I have again the example of just measuring the first qubit. And then, for example, I define as the output of my quantum algorithm the probability of this qubit being in state 0 or 1. And you see here again this matrix that represents this measurement matrix or this observable that represents such a property. And so what you see on the lower right, you have seen it before, is kind of like this vector matrix, vector multiplication that gives me out of this mathematical description basically the probability of seeing the first qubit in state 0. And this I have now defined as the result of my algorithm. And obviously I can define lots of stochastic statistical properties as an output, but this is a very common one as well. So putting it all together, so everything that I want you to know from this section is in some sense that there is this like kind of empirical level of samples, and we can understand quantum computers as producing just a set of samples. But on the mathematical level, we cannot describe these stochastic systems with probability distributions. We need something that's called a quantum state. And quantum algorithms are basically just evolutions of these quantum states from a very, very simple system to like a more complicated quantum state where sampling gives you like more interesting distributions. And what I also want you to take away is that these algorithms that we use, they can encode inputs, they can encode 3 parameters, which means that our distribution in some sense or our state depends on these parameters, depends on these inputs. Okay, so finally, like as like another recap, so quantum computers sample bit strings that are generated in kind of a slightly different way. You actually, to implement quantum computers and actually simulators, and we see like an example like in the next section. So simulators are in a sense just matrix vector multiplication. And thirdly, quantum algorithms can make the statistical properties depend on data or trainable parameters. Okay. Hello, welcome back. I hope you liked the little introduction into quantum computing, which was probably very unusual to the normal introductions you might have seen before. Before we go into the Q&A, I just wanted to tell you, you can also obviously like get your coffee and like take a break. Maybe we have a couple of minutes of proper break at the end of the Q&A here. But I also wanted to say, if you want a little task, like a little Gedankenspiel experiment, you can think maybe about the question that we try to answer in the next session, which is how can you use these quantum computers that we just introduced as samplers from bit string probability distributions? How could you use them for machine learning? If you were now the QML researcher like 5 years ago, what would you do first thing? What would you ask? And if you want, you can just post in the chat and share with us.
Okay, maybe we first start with questions related to the representation, the data representation. One was again about the problems with big data. So can you please explain why we can't run large data sets through today's quantum computers?
Oh, yes, I also saw there were a couple of questions about, how to encode data. And I think after this block, it's much easier to answer them. So maybe very specific about this one, because it was asked before. So no one says, or maybe I hope you didn't get me wrong. It's not the case that you can't encode big data sets into a quantum computer. I can give you an example. You could take one of these subsystems, one qubit, and you take your big data set and you rotate the qubit by the first feature and then by the second feature. By rotating, I mean you apply some physical operation that does something to the qubit. So you could, in theory, put an entire data set into the representation of a qubit. Whether this is a good representation or not, I doubt. So definitely you can encode big data sets into quantum computers, but the speedups that people were hoping were very often set up in the way, like especially a couple of years back, that the data encoding is a bottleneck. So often they were going for speedups where you can do things in logarithmic time in the size of the data set. And you can imagine that then you have to make a case for what you do with your data if you can't even read them in, which takes linear time. So this was kind of the idea of this. But maybe more in general, to clarify a bit this encoding question. So why this is so vague in the tutorial, you will see a few examples, but in general, this is always a black box that we leave kind of open, is because the community hasn't answered this question yet. And I think we haven't even put a lot of resources into trying to answer this question. What is a good encoding of classical information into quantum states to do machine learning? So we've done a lot of the pipeline around it, the quantum gradients, the models, whatever. But this encoding question is very important and it's so open. But there were, obviously, people had a lot of ideas and people ran with this. So for example, you could do, one of the first ideas was, you could take this object psi, so this vector that replaces the probability distribution. And you could, for example, take just a classical data point, like a feature vector, and use a quantum algorithm such that you start your algorithm for machine learning with a state vector that is exactly identical to your classical vector. So in some sense, you literally you almost like think of features in your feature vector as probabilities, but not probabilities in this sense, quantum amplitudes. And then you kind of apply an algorithm to this vector, which is obviously an exponentially compact representation, but the algorithm will still be linear in the size of the data, if that makes any sense. Another one would be, you could do a data encoding where, and this pertains to another question about bit representation, you could convert your features into bit strings. And now you could start with a probability distribution of your quantum sampler, so to speak, such that sampling this bit string has probability 1. So this is what we kind of call basis encoding, or qubit encoding, sometimes called. But nowadays people do a lot more complicated things. So they encode things into physical operations of some sorts, and then they ask what happens with these things. So there's a lot of ideas out there, but yeah, this is not settled yet.
Okay, thanks. Then there were questions relating to the hardware. So what, in your opinion, is your opinion on different quantum hardwares? Do you think there's one which might be better than others?
Yes, so this is a hard question. Aram, I'm also inviting you because so Aram sits probably on lots of panels where he gets asked this question. And so I think the generic answer is always like, the race is still open. So there are different, especially companies, but also labs, that try different paths. And the one that has yielded the first result so that you can, scale up the number of qubits to like 10, then 50, maybe like 100, was so-called superconducting hardware. And the problem, so you never know, so the hardwares differ very much in where the bottlenecks lie. So for some, it's very easy to like make 10 qubits communicate, or maybe even 100, but it's very difficult to make 1,000 communicate with each other without the effects that destroy the quantum resource or the coherence. Other approaches, so for example, the company I work for, we build a photonic quantum computer where we do not even have a qubit yet, or the equivalent of a qubit, because everything is a lot more complicated there. But once we have one, we're pretty sure, or we have a few, we're pretty sure we can produce a lot of them. So this is why it's very hard to see what's good, what's not. And every hardware has its problems. I mean, there are more problems than you can imagine in every piece of hardware. But Aram, I don't know if you want to add a bit, because yeah, I mean, having you here, we should use this.
Yeah, I guess one thing to keep in mind is like what people should look at besides number of qubits, and that's the lifetime. But you want to know like the lifetime of a qubit measured in terms of how many gates it can perform. So superconducting qubits are very fast. They have like nanosecond gates, but they also decohere very quickly. And ion traps are very slow, but they decohere slowly. And kind of in each case, the number of gates we can do during their lifetime, the lifetime of a qubit is like 100 to 1,000-ish, depending on how it's done. But, they're sort of different time scales, but they both end up kind of comparable. And then these dark horses like photons have huge scalability advantages if they can get over some initial hurdles. So as Maria said, the ones that got to a moderate number of qubits may or may not be the ones that will get us to 1 million qubits. So it's at this stage, it's really the race is still open and people are pushing in all directions.
Okay, thanks. Then there was a question if quantum computing is suitable to deal with computational algorithms better than usual traditional algorithms, as for example, quantum simulated annealing. And if there are other domains in which quantum computing has a significant advantage.
Oh yes, maybe I may take this as an opportunity to pick up this question about quantum advantages now again from one level deeper. And so the biggest confusion I think of, for example, my students, but actually also myself when I started, is that when you think of quantum computing in general, you always think, oh, we know quantum mechanics, there's something different, right? And we can describe this by theory. So now why don't we take this different and put it into a computation and then build an algorithm from it, and then we know something is different. And it turns out this is like, it's so much more complicated than that. And so let me try to give you a couple of pointers to kind of show you where I can confuse you or where things open up into more complex topics. So for example, and I'm not an expert at all on this. This is like quantum foundations. You need to study a completely different branch if you want to get good at this. But so in quantum mechanics, there are lots of notions of what's non-classical. And we do not even know very often the definition or the connections between those notions. We do not often know how these notions can be measured. So for example, sometimes you have a notion of something that you can't even define for like lots of qubits or something like that. And we often have only a vague knowledge how these notions correspond to quantum computing. For example, so we spoke about entanglement as a resource, and this is a very standard one. There are also like resources that are similar that are called discords, so non-classical correlations that are not entanglement, but so there are lots of those around. There's the notion of non-locality. You might have heard of the spooky action of a distance from like Thal experiments and so on and so forth. Then there's something called non-contextuality, so that quantum probability distributions, so this has to do a lot with measurements, that you cannot define two random variables in some situations at the same time. So for example, the position and the momentum of a particle. I know I'm going very deep, but I think this is really important. So this is this idea of non-commuting measurements. You know that we need matrices to describe this, because if we measure the one first and the other one is different than if we do it the other way around. And also there was a question on kind of the collapse of the wave function. This is this idea of, if you measure something in classical probability theory, you decrease your state of uncertainty or your lack of knowledge. But in quantum theory, you can measure something, you decrease your state of uncertainty in one measurement basis, but you increase it in another. So this is all the strange thing that's going on. So now all of this is kind of like quantum mechanics and a lot more. And now how is this used in quantum computing is very unclear. So for example, you can say, so in quantum computing, we're often asking like, we want provable speedups compared to classical computer, which is still something completely different. You could use a quantum resource, but you can simulate it classically. So for example, this interests you, look for the term Clifford gates. Clifford gates are gates for quantum computers that introduce entanglement, all of those things. So everything nice in quantum, but they can be simulated classically because there's like algorithms and there's a special structure to them that makes that easier. Yes, so it's very unclear how these things, even like I think yesterday on the archive, there was a paper on, contextuality is needed for quantum computing and might be the resource. And so everyone is still, discussing this very much. So it's super interesting actually to talk about this. And then lastly, maybe let me add this little point. So in quantum computing, how we usually do it, we often don't talk about contextuality and measurements and all of those things. We just, as I said, in the simplest case, we just think of, measuring bit strings. And what we think about is that the probability distributions can be prepared faster than on a classical computer. So if you look into these so-called quantum supremacy experiments, then you will see very often that what they do, they just like propose something we can do on a quantum computer that prepares a distribution, which it's very hard to sample from on a classical computer. Very often these distributions are completely useless. So they're almost uniform, or they have properties that make them very hard to put into applications. And so lastly, quantum machine learning is one of these areas where we now have to like come from, what we know from quantum mechanics. We have to take these things that we know about quantum computation, and we all of a sudden have to think about usability, which is introducing a completely different question. And sometimes you have to let loose the advantage a bit to get the usable aspect. Sometimes you have to, put the usable aspect away to get actually a provable quantum advantage. So to combine all of these things, something is like a blanket that's always too short somewhere. And so this is why I can't just stand here and say, you use interference and parallelism and then your machine learning will be better. So this is really, really hard. So this was a long speech, but I hope, kind of like clears a bit up why we're not just delivering this thing to you that you want to know about, can quantum computers do everything better? The answer is definitely no. But what they can do better is very, very, very hard to pinpoint. And you have to talk about situations and not just generalities. So a bit like if I ask you, are kernel methods better than neural networks, or the other way around? I mean, try to answer this like properly. That's actually also hard. Oh, sorry. I don't know, actually, if we want to go into break or
into what?
Into a break, or if we still want to.
I think we have 4 more minutes, if I'm not wrong. So we can continue maybe with, there was a specific question. How does one understand the difference between superposition versus mixture of probability distributions?
Sorry, can you say this again? Because I just saw the...
How does one understand the difference between superposition versus mixture of probability distributions?
Yes, maybe the most simplistic answer I can give is a superposition has the potential to interfere amplitudes. Interference was the thing where you take like negative signs or complex values, and you can actually like combine probabilities to, for example, cancel them out. So this is maybe the simplest way. And in classical mixtures, you cannot do this. And when you write down the maths, you can actually write this down quite elegantly that you see this. You can do classical mixtures of quantum states. So you can put the classical stochasticness on top of quantum states if you have uncertainty about which quantum state you're in. But the quantum states themselves in superposition is something slightly different. So that is clear. I was just like, I was just looking at the chat. Someone said like very hand-wavy explanation. I do not like it. Yeah, I don't like it either. But that's research, right? If you have any, if you have a big question like that and you have a simple answer, you're either lying or this is not an interesting research field. So, yeah.
All right. Okay, then given the inherent stochasticity of quantum computers, is it possible to achieve reproducibility?
Yes, so how you set up most algorithms, we see this actually now. It's a very nice, like, how do you say, bridge. So since you just have like samples that you always get, you have to do some tricks or some post-processing or some definitions that make things deterministic. So then if you want to, for example, have an algorithm where you have a deterministic outcome, you have to say, for example, I take the bit string as an output that, popped up most of the times, or you say I take an average value of something. So you have to like use some stochastic property of your distribution as the outcome of your algorithm. So there are different ways to do this. So we see one now, I hope.
Another more mathematically specific question: what are the major challenges in performing optimization in high-dimensional Hilbert spaces, and how can we overcome them?
I see. I was thinking you referred to kernel methods, which we go into this. The question of barren plateaus, for those who are interested, so this is this idea of if we optimize quantum states, so which we do when we optimize quantum circuits, this is now like then a lot of research is done on that gradients vanish. I personally have a very particular opinion about, I think this research is very interesting, but at the moment the models people analyze are often as expressive as quantum computing itself. So we're looking into a very, very big class of models. And I think that these vanishing gradients have a lot to do with the fact that we do not pick our models precisely enough. But this is an opinion, so this is a big debate. So I'm not the best person to comment on this.
Okay, thanks a lot for answering these questions. And I think we are going to answer this question answering session now. And let's look at the...
Yes,
so we have a video again, right? In the next...
Yes, I promised you a little break. I hope you don't mind, but we have a bigger break after the next Q&A. So, and then...
Okay.
So welcome back to the third part of the NeurIPS 2021 tutorial on machine learning with quantum computers. And in this part, we want to leave the slides and we want to leave the theory for a second, and we want to get into coding because, you know, code can never lie somehow. And so the first thing I want to do with you, I want to do a bit of a live or recorded live demo. And I want to take what we learned in the last section and kind of like turn it into code. I want you to see how it actually looks like when we evaluate cells and run quantum computations. And then in the second part, you get to play around with a pre-coded notebook. And in this pre-coded notebook, I want to show you the idea of taking these circuits and turning them into machine learning models, or interpreting them rather as machine learning models. And you will find two examples. There's one example where we just interpret the samples of, you know, bit string samples of a quantum computer, so these raw samples it produces as a generative model. And the second example fits a little sign function where we have more like a neural network, like a model for supervised learning that encodes data and returns a prediction. Okay, let's get started. I'm very, very nervous because even if it's recorded, live coding is never fun, but I hope all the mistakes I make, we can learn together from them. So the framework that we will use and install, first of all, is called PennyLane. PennyLane is a software framework for automatically differentiable quantum computation, and I'm like part of the lead developing team since like many, many years. So this is like really something I know quite well, and I'm happy to share with you. And so first of all, it's an open source library. You're very welcome to join the contributors, or there's a lot of like ways like community calls or like hackathons that you can get involved in. The idea of PennyLane is that it basically navigates, on the one hand, backends that are quantum computers. So, for example, you can have these local simulators, remote simulators, or remote hardware devices that I spoke about earlier. And PennyLane connects them to auto-differentiation frameworks used in machine learning and, you know, in optimization. And at the moment, we have connections or you know, interfaces to TensorFlow, PyTorch, JAX, and AutoGrad. And AutoGrad, maybe not so many people of you know, it's a package that was like based on making auto-differentiation feel like you're just coding in NumPy. And JAX, and also I think originally PyTorch, were based on this package. Unfortunately, it gets you know, deprecated very soon. So yes, but yes. So this is PennyLane. You can check out the webpage. You find a lot of demos, and maybe if you want to, are more the coding person, you will find a lot of the stuff that I was talking about. And then the documentation you can check also on the webpage. Okay, let's start. We've got it installed. Let's import it. And then I won't only import PennyLane, and this is already very suggestive of like that PennyLane is used for quantum machine learning a lot, this QML short form. I will also import a wrapped version of NumPy. I'll tell you in a second why. And let me call it PNP so I don't get confused. And so this wrapped version of NumPy, if you are used to JAX coding, this is exactly the same. So JAX also wraps NumPy. So this is like kind of this idea of extending this AutoGrad package. And it basically just means make NumPy fit for automatic differentiation. Okay, cool. So first we want to specify a device. So the device that I use here is default qubit. So this is the simulator that ships with PennyLane. It started, so the name implies like it started as a little kind of default simulator so people can start with something when they download the package. But now it's actually quite a big one. It has kind of sub-devices or sub-backends where an entire quantum simulator is programmed in TensorFlow, JAX, AutoGrad, or PyTorch. So that means you can do your entire quantum simulation in those auto-differentiation libraries. And then you can obviously backpropagate through them as well. Then we do have to specify which qubits we act on. And so we can give them names, but for now we just use the default names. I will have 4 qubits, and qubits are called wires in PennyLane to just be a bit more general. And then we also need to specify the shots, the number of shots we want. So shots, remember, were the number of samples I draw from a quantum computer. If a quantum computer gives you bit strings by measuring qubits, then the shots are how many of these bit strings you actually get per computation. But obviously the algorithm has to be run now 10 times every time. Okay, and then now we can specify the quantum computations. So this is actually like really a beautiful part of PennyLane because quantum computations are just defined like Python functions. So they have a really, so the entire framework has a very functional look and feel. And so basically like I can now specify a qubit unitary. So this was this big matrix that I can use to kind of define what circuit I want to run. But I also told you that no one actually does this, and this matrix like scales exponentially fast with, you know, all the amplitudes that I have in my system. So what I actually do, I specify like smaller gates that only act on subsystems. So for example, I use a famous Hadamard gate on the first wire. And secondly, I use a Pauli X gate, or Pauli, no, just a Pauli X gate on the second wire. And measurements, so now I want to measure my circuit, and measurements are always like specified in the return statement. And in this case, I want to just get the raw samples out. So now, if I just have this is just like nothing other than a Python function, but I want to turn this into something that can run on a quantum device. And the way I do it, I wrap this function with like a lot of logic that happens like on the outside. And how I wrap this, I use a decorator in Python. And the decorator is called a Q node because we kind of understand this as a quantum computational node. And in PennyLane, these quantum computational nodes are differentiable. And so what I do in this Q node, I just have to tell what device I want to bind this quantum function or quantum circuit to. Okay, cool. So now I've got a kind of like a working quantum computation node. And before I kind of use it, I want to first show you how it looks like. So there's a little draw function. And as I said, everything in PennyLane, or most things, are functional. So what the draw function does, it takes a circuit, it spits out a function that wraps the circuit and changes it into like a little drawing. And what I have to do to call this function, I have to give it the same arguments than the Q node. This will become probably clearer in a second. And so this is like kind of my little circuit in the diagram I use. Okay, now let's run the quantum circuit. So now I'll run my quantum computation. And what I get out are, and shouldn't surprise you, is basically a 10×4 array, and it contains bits. And what you see in each row is basically one bit string sampled from the quantum computer. I asked for 10 shots, so this is why I've got 10 of these samples, and I asked for 4 wires. 2 of them I didn't address, so they're not here in the drawing, but so the first 2 are addressed. And you see that I didn't do anything with the last 2 wires, and they are actually still in state 0, so nothing really happened here. And you can also nicely see what the Hadamard and the Pauli X gates are doing. The Hadamard gate puts a qubit into what we call a uniform superposition. So it is a quantum state that basically has a probability of 0.5 to be measured in 0 and 0.5 to be measured in 1. And the Pauli X gates, what we call it, like rotates the qubit or flips the qubit. So when you start in 0, it will afterwards be in 1. Is exactly what you see here. Okay, cool. So now let us also go one step further and introduce parameters to this quantum computation. As I said, some of the gates we can parameterize. So let's replace, for example, the Pauli gate with a so-called Rx rotation, and now we parameterize it with like some kind of weight parameter W. Okay, let's run this. And now I have to give my circuit. So first of all, in the drawing as well, I have to give my circuit now this parameter. I have to specify how far shall I rotate. And so you see now this parameter showing up here. And now my samples all of a sudden depend on this parameter. You see if I tune it up, actually this, so remember this gate, the parameterized gate acts on the second qubit, and the second qubit starts showing more and more ones the higher the number. And this is actually quite sweet because this is why it's called Pauli rotation, because if you put something like an angle of pi into this, you will see, oh, I don't have an NP, oh sorry, I kind of imported NumPy in the wrapped version, so I need this one here. So you see that the second qubit actually is in state 1 all the time. So somehow what happens here, a rotation about pi in the Rx gate rotates the qubit from 0 to 1 in some sense. We won't go deep into this, but this is quite neat to know. Okay, cool. And now you've got all the ingredients to actually have a generative model, and you even have a trainable generative model if you think about it. Because we can now interpret these bit strings just as data that are sampled from like some kind of algorithm. And the interesting part is here that I don't use a random seed, so classical randomness, and this sounds a bit more mystical and more powerful than, like I really intend to say. But in some sense, quantum randomness is used here as the randomness in my generative model. And so in the tutorial that you work with, you will see that you can use this to, so what we do there, we use a circuit that people use a lot in experiments that were very, very famous to measure non-locality, so-called Bell states. You might have heard of Bell inequalities. And these Bell states we will use then to produce our hand-coded generative model where the first 2 bits and the last 2 bits are 100% correlated. Okay, great. Let us go one step further. There's only like a couple of more things I want to show you that you also like know already from the last section, but that you need now to interpret quantum circuits as not generative models, but you could call them discriminative models. But what I actually mean is just models for supervised learning. So for that first, I want to encode something else. So let's now add an X. So this will be like my input, for example. So I just use, I'm literally making this up here, and I'm making these gates up, and this is actually how people in quantum machine learning usually do it. They just use the gates that they know from quantum theory. At the moment, we have no clue if these gates are the ones that are good for these models, and there's very few studies, and embarrassingly few studies actually, that really critically ask, isn't there a different building block we should use? We just use the one that we know and that our hardware knows. So there's just a little critical side note. Okay, so I don't know if the circuit I'm coding up here makes any sense, but I just make it like a little bit more complicated in the hope that something interesting comes out here. I put in another 2-qubit gate. Okay, after some blind coding. Okay, now I've got just a circuit that now encodes inputs. And so what we get here, you remember, is kind of a quantum state that depends on X. I want to actually show this to you. I don't know if this will work now, but I can, since this is a simulator, I can hack something. In a real device, I can never get the state, right? The state is a mathematical object. The state was the thing with the complex valued amplitudes. But in our simulators, if I'm not mistaken, I can actually give you, if I now put another input, so this is my X value, this is like my Y value. This works, yes. So this is now here the quantum state vector, and you see it has these complex values, and some of them are non-zero, so on and so forth. Okay, cool. But what I actually want is now something else. So I want to stick with real devices, or more or less at least real devices for now, where we don't have access to this crazy state that also grows so fast with the number of qubits. I use an X bar measurement. So this is this measurement, remember, if we want to, like, in real life sample, and then we take some statistical properties of these samples. For example, the probability of the first bit being in 0 or 1. You remember that in the mathematical formulation of quantum mechanics, we can get this value by taking a row vector times a matrix times a column vector. And so this is called an expectation value measurement. So this is what I'm demanding here, and I have to specify this matrix. And so I want to now specify a matrix that kind of answers the question, is the first qubit in 0, 1? So it gives me the expectation of the first qubit. I don't know if anything interesting will come out of the circuit, but let's kind of draw it for a value of, I don't know, -0.4. I'm running out of numbers here. Okay, so this is now my circuit, and let's see if anything interesting happens here. Okay, cool. So you see here 2 things. So the first thing you see is that there's some tensor. You already saw this in the state, and there's this requires grad, and we get back to this just in a second. So this is already a trace of auto-differentiation. Something happens here where gradients are defined. But for now, I just want to like stay here for a while. You also see that there's a minus here and there's a negative number. And so this is just like a convention that the Pauli Z matrix doesn't really specify the measurement of the expectation of the first qubit if we interpret the qubit as being either in state 0 or 1, but instead -1 or 1. So it's basically just a rescaling here. And this rescaling is pure mathematical convention. So if you see a value here, then you have to interpret this as a value between -1 and 1. And if you want a probability, you just have to like shift the interval to from 0 to 1. Okay, cool. So that's the first thing. The second thing I want to show you is if I run this again and again, I always get a different output. Why is that so? What happens in the background is the computer like samples shots, only 10 shots, and then it estimates this expected value of the first qubit. So if I increase the number of shots, what you see happening here is that this value should become more and more, the variance should like get smaller and smaller. Okay, it doesn't get like super smaller, but at least a little bit. And now since we have a simulator, we can do another little trick, which is really nice. We can actually set the shots to none. And that means that our circuit will always spit out the same value. Or in this case, this seems to be a really boring value. Let me see if I can make this value more interesting by changing my first input. Yeah, okay, so there's something a little bit more interesting going on here. Okay, cool. And so this was basically it. We now have, in some sense, something we can use as a machine learning model. So obviously in real quantum hardware, we will always have shots, but we can take a lot of shots and we can get pretty accurate estimates for outputs. The rules of how, the variance, shrinks and shrinks for higher levels of shot, this is just normal stochastic probability theory. So you can just use all your like knowledge from there. And so these shots also, like you can repeat quantum computations usually very, very often, very quickly on quantum hardware. So we can get like 10,000, 100,000, sometimes a million shots actually really fast. So these estimations, you have to count them into your considerations of runtime, but it's usually not like a really, really big headache. Okay, cool. So the last thing now I want to show you is now that we have a model, but I promised you that we're in an auto-differentiation framework and we can train the model. And you see like how we can train a model like this to kind of like fit a sine function. This is like not coincidence, like these rotation gates somehow have something very Fourier-like going on in them. And so like these experiments are always quite easy if you just use sine and cosine functions as graph truth. So much just as a comment for that. But so when you fit this, you will use stochastic gradient descent. So I have to show you basically how to get gradients out of your quantum computation. I think there you will see this in JAX, but here I just use the framework that I have. So for this, I have to, at the moment, I was a little bit sloppy. I just put in like normal float values, but I actually want to get now a little bit more precise. And I want to define these scalars as numpy arrays. And remember, we wrapped numpy because then we can use something that we can make differentiable. So let me just like, kind of recode this. And now what I want to do, I want to use, and this works very much like in PyTorch, that requires grad flag. And my X is kind of my data point. So you should be used to this, that we said the data doesn't want gradients, but the weights want gradients. So let me not talk and code at the same time. I can't do this very well. Cool. So now my weights are trainable. And let me now run the circuit with X and W. So it should actually not have a different outcome. Yes. But now what I want to do, I want to specify the gradient. And in the autograd interface, so in TensorFlow, obviously you specify gradients with a tape. So it's exactly how you do it there. In PyTorch, you do this like gradients get attached to the arrays. But in autograd that we currently like are using here, we have basically a penny lane function that's called grad that gives us the gradient. But it actually works also in a functional design. So it gets us actually a gradient function. And now this function, let me actually do this like this, because this might be a bit less confusing for some of you. So I kind of catch this function, and then the function, the gradient function, I can evaluate at different points. So I want to now evaluate at, let's say just X and W, because we've got those. And now you see I've got a gradient of my computation. The gradient is vanishing here. This has nothing to do like with vanishing gradient problems as such, because my circuit is very small, but basically just by how I picked the circuit. So basically you now have all the ingredients to turn quantum computations into trainable models, generative models or discriminative models. And you also know you can do this on a lot of quantum devices. You can do this on with a lot of like classical interfaces, so your favorite programming interface. And then I hope like in the notebook that you will now play around with, you can explore this idea a little bit more concretely. So welcome back. I hope you enjoyed to see a little bit of code in a couple of lines. For this Q&A, again, this is the last one where I give you kind of like an alternative task, but you can also obviously go on your break already. We will have a break after this anyways for a bit longer to just stretch a bit. But if you're keen to play yourself and not maybe listen to questions, I posted a link to a notebook in the chat. And so this contains a little bit the logic that I was showing in the video, and also goes a little bit beyond. So you will see examples of how to really take a circuit and turn it into a generative model using like some kind of like entanglement capacity or like creating null states. And then you will see the deterministic model. And in the end of the notebook, you will see how you can optimize everything. Let us know if things don't go well. Okay. Cool.
So do you want to, while some people are playing with the notebook, do you want to answer other questions, or how should we?
Oh, yes, I thought we could do this in parallel, because you know,
sure.
if you want to listen to questions or if you want to play with the notebook, you can just decide.
So I guess one question that a few people had was about how do you, which actually you've written some papers on, is how do you backpropagate through a real quantum computer?
Yes, and can you backpropagate through a real quantum computer? So the
can
answer,
you? Yes.
Yeah, exactly. So the answer, if you know a lot about backpropagation, should be quite clear in this case, finally. And the answer is no. So not that we know of. So to give a context, if you have a neural network, if you compute a gradient vector, you know, that has all the partial derivatives of the parameters in it, so it's a huge vector, you usually just have to run your network maybe forward and once backward, as you know. So the beauty of backpropagation is not necessarily only that you can automatically, you know, compute gradients, but also that you can do it extremely efficiently because you share information. These tricks that people use in automatic differentiation, we've thought a lot about this in the team at Xanadu, seems to be very incompatible with what you do in quantum mechanics, because you can't really like measure out a state at some stage, because then this collapse of the wave function or whatever happens. So you change your system in some sense, or like, you know, it's really like invasive in quantum mechanics. So you can't just like measure part of your system and then use them to compute different gradients. So it's a very, very hard task. What does that mean? This is actually or leads to a detail that people who do quantum or optimization of these variation circuits are shockingly often not aware of. And this is that optimizing quantum circuits or models used as quantum circuits is not as efficient as optimizing, for example, a neural network. So again, a neural network needs, let's say, one shot to you know, get a whole gradient. A quantum computer, you need as many measurements, or you know, as many runs of your circuit, let's put it like that, as you have parameters in the network. So you very likely can't scale it as much as normal neural networks. So in some sense, we are like then dependent on, so this, if we scale this up, this will be only efficient if we have applications for which the number of parameters doesn't scale as crazy as with neural networks. So billions of parameters is probably out of the question, because we get this like linear additional overhead in backpropagation. I hope that was clear.
Yes. Although I guess if you had more coherence, you might be able to do a little better, right? We're thinking very Nisky, right, about how you don't want to run it, you know,
yes.
Don't want a lot of extra qubits. Like you could do some of these Gillian kind of tricks, right?
Yes, you could probably do a lot of tricks to kind of like get information. So there are lots of ways of how to not destroy a complete quantum state if you measure. I guess you referred to this, right? That you can get information out of your system and put it. This would be super cool research to really look into. The point is kind of like, let's put it like that. If you look into the mathematical theory of automatic differentiation, so like a bit more the formal theory, it seems very, very hard to reproduce this with quantum mechanics. But you're right, like it's a big open question. If someone can tell us how to backpropagate as efficiently as, and you know, backpropagate through a quantum computation, not only like get a gradient out of quantum computation for larger backpropagation, that will be a $1 million paper, I think.
Right. So one other, so one other question is, well, should we move on to a different question or discuss this one more? I guess one other question is, how do you learn nonlinear mappings of unitary gates? It's quite a broad one.
Okay, that's a really broad one. Let me just is there any hint on, so how do you learn? Oh, I see what you mean. So that's a super good question. It's also really hard to discuss it if you don't have a board and you just sit down and you have a couple of examples. So I'm also giving a bit of a high level answer, but it depends very much on your data encoding strategy. If this unitary transformation, and the question is really good. I mean, it's very sharp observation, right? But if this unitary transformation, which is linear, does something nonlinear in the data. So think about it. If, for example, your data is encoded in the quantum state vector, and then you do a linear transformation on it, you will only have linear transformations on the state vector. If you do a measurement, you might get slight nonlinearities because you remember you've got this quadratic form, so you get often a quadratic factor or something. But indeed, this, and lots of people have done this at the beginning. As I said, they encode their data into the state vector, then they do lots of unitary transformations, they learn them, and then they're surprised that they don't get very powerful classifiers, but they're just linear. But think about it, if you now encode your data into other properties of the state. So your quantum state is basically a vector that depends on X, but is not identical to X. Then your unitary transformation, even if they're linear, they will act non-linearly on the data. So it's exactly like with kernel methods, and we'll get back to this actually in the next session. So where you kind of if your embedding or encoding of data is non-linear, even if you do only linear things afterwards, the whole function that you have is non-linear. So I think this is maybe the clearest one. This is all.
Right. Good. Yeah. And I guess one question that was answered in the chat, but maybe is worth discussing more, is how expensive is it for a classical computer to simulate quantum gates? Because we see that these Google experiments, 52 qubits, you can barely simulate, but maybe that was doing one thing with 52 qubits, doing their particular circuit.
Yes, exactly. So in general, the rule is quite simple, right? If you have no knowledge of what's going on, what you need at least is a simulation that represents, so if you have n qubits, you need a 2 to the n dimensional vector filled with complex numbers. So you've got a couple of quantum factors as well. And you need to multiply. So if you want to really say, okay, I'm not applying this gate, this means you multiply this with a 2 to the n times 2 to the n dimensional matrix. So you see that your simulation space just grows exponentially with the number of qubits. And there you get, I mean, if easily, right? If you say 2 to the 50, I mean, that's a computation can't be managed. But then there are thousands of tricks. So in every situation, and you have to read the fine print on these simulation capabilities. So if you don't have a lot of entanglement in your quantum states, then there are tricks to use, for example, so-called tensor networks. So for example, Penny Lane, but also AWS systems. So lots of the quantum software have tensor network simulators. And what they do, it's a bit like in classical machine learning, you don't really write down a probability distribution, but you factorize it. So you express it as kind of, this is also a bit shortened, but you kind of have an ansatz that captures all the important bits, but it's a more compact representation. And then there are things I refer to the Clifford gates. So if you do not have certain types of gates called the non-Clifford gates in your circuit, you might also get away with much fewer resources. So if someone claims they can simulate, I don't know, 70 qubits, you'll always be in a very, very special case. And so it's a lot of fine print. But I think so on my laptop, when I do something with just a default simulator, I don't know, I get into trouble after 25 qubits. If you then put it onto a cloud somewhere, 30, 35 is still fine, but I think, I don't know, above 30, it gets nasty. Especially if you do machine learning, because you have to send your circuit, optimize, come back, compute all the gradients. It's a crazy pipeline.
Right, which puts us into an interesting situation where we just have to run it on quantum hardware and figure out what the results,
Yes.
This field becomes more empirical.
We need that, yeah. But at the moment you run it on quantum hardware. Yeah, at the moment you run it on quantum hardware and you run into, I mean, you can write a paper only on how to fix the errors on the quantum hardware. So this is a completely different, so you can do a lot of things by the clicking something. Nowadays, I think the pipelines are very easy, but to get this to work fast enough and I think if you good data is actually still, a whole research project for single computation, I think, in many cases. But interesting.
Definitely. The last question was about comparing with Bayesian neural networks and wondering, in a Bayesian neural network, part of the challenge is that you have to learn a distribution. And is there a similarity between that difficulty and some of the challenges in training quantum circuits?
That's maybe a nice analogy because yes, in Bayesian networks you have to learn a distribution. Maybe we'll get back to these barren plateaus if you remember. So, for example, when I was saying at the moment lots of theoretical work is done not looking at very specific models but at very general models. And if you use Bayesian networks as a nice example, Bayesian networks are not just general probability distributions, they're very specific ones with specific correlations and specific limitations. So a lot of theoretical work pretends we do not have these limitations, but we just ask, okay, we have general distributions, how can we train? So I think actually the example to think of training a generative model or training learning how a probability distribution has to look like is really great here. And also maybe I hope from the little coding example, you realize, so associating quantum circuits with generative models is a lot more elegant than doing anything else. So, you just don't have to do much other than that. It just fits in, and then you can now start asking, which distributions, for example, could we learn very easier. The problem is if you have to do theory building with generative models, like most of you know, you're in big trouble. If you have to really fit distributions to other distributions, there are obviously thousands of ways. They're quantum GAN applications and all sorts of things of how to do this. But it is often much harder to study theoretically than the supervised learning problem. So this is why a bulk of quantum computing or quantum machine learning still looks a lot into supervised learning. A lot of people say maybe one day we'll just do generative stuff, and I could see this happening as well.
Yeah, that makes sense in terms of, if quantum computers are good at sampling from unusual distributions, then that makes a lot of sense. One question, I don't think we answered this from a while ago about how expensive is it to run quantum computers on real hardware, and the landscape here seems to be shifting so much. There's something you can get for free and something you can pay for, and many different companies with offerings.
Yeah, I was wondering what you mean by how expensive it is, if you really mean cash, because a lot of the quantum, so for example, the AWS system, you have to often pay, business models of big companies start going around making you pay for each run, which is really, it's super scary because you sit there and you have to click a button, and even to test your code, so very often software frameworks, and we try to build this, I know this because we try to build this in Penny Lane a lot, is, you would like to tell your software, please make a dry run and then tell me how much it costs, but to even estimate that is often really hard. So so it's very scary to run nowadays on backends where you have to pay. I think there are though a lot of them, so the small computers are still accessible for free, right? Definitely a quantum experience. You can get quantum.
Yeah, I know IBM makes some available for free. I don't know up to how many qubits.
Yeah. I assume this will get more and more tightly locked up, unfortunately, because I guess at some stage those groups have to also motivate why they are providing this work. So the larger ones probably will be paid for services. A lot of companies make contracts with, as I said, with academic institutions. So if you are a big academic institution, very often you get free access or, for pioneering studies and stuff. So there's still a lot of space at the moment.
Right. So yeah, let's see there are some questions about, which one would you like? So do you want to talk about tensor networks or about encoding the data into the gates instead of the qubits?
Yeah, let me quickly let me actually do both. One of it. So the one about the tensor networks is, you mean is it beneficial to use low rank tensor formats such as MPS or TT to simulate larger quantum networks for QML? Is it used in?
I don't know what TT means. Tensor matrix product states, and then TT.
Tensor trains, no?
Tensor, yeah.
That's one. Yeah. Yes, and so that was what I was saying. Like a lot of quantum frameworks give you backends that simulate quantum circuits by tensor networks, and that can be a lot faster. Funny enough, it is not always the case. So really, by now, if you really want to do large-scale simulations, you have to know a lot about your hardware, a lot about your circuit, a lot about the limitations, and then you can fit everything together, which is really, really hard to get all right, even if you are, a software developer, like to get this all like together. So yes, so this can help. In Penny Lane, so at the moment, I don't know if I'm disclosing something here, but like, so we are looking at, we had like a small tensor network device all along, but we're now looking into making this a lot bigger. And a lot of questions now pop up, obviously, because, for example, Penny Lane wants to make everything differentiable. So what does that mean if you make tensor contractions differentiable? So there's a lot of open questions for research. So when I say like quantum machine learning happens at this level of, machine learning research, but there's a lot of actually hardware research that popped up, or hardware and software research that actually popped up that's super interesting as well. This is one of those. To jump into the second question directly, Aaron?
Sure. So do you want to answer the one about should you encode your data into the circuit and gates instead of in the qubits? I guess that also connects to kernel methods in a way, right? Yeah.
Yeah, that's actually, I must say the quality of the questions that you ask is so, I don't know if you're all expert, but it's so spot on. I mean, I didn't expect anything else from the audience, but I'm really, really impressed. So yes, so there's a strange thing about, so starting your computation with a certain state, maybe let's say it's not the most simplistic one, but something else, and then applying a quantum circuit and then doing a measurement. And mathematically, you can, as some of the lectures also said, you can absorb things into each other. So for example, you can say, I'll start with a simple state, but now apply a complicated circuit and a simple measurement. Or you can say the simple measurement becomes complicated if I absorb the circuit into the measurement. So the representation is such that we have, we can interpret things in a different way. Funny enough, recently I realized this is actually when you do physics, you learn about the Schrödinger and Heisenberg picture. And this is very similar to this. Like, do you think of your state evolving, or do you think of your measurements evolving, for example? So why I'm saying this is to encode your data into a state or to encode your data into a circuit is theoretically one and the same thing, I think, in most situations, because you could just say your circuit is a state preparation routine that prepares a state. So you encoded it into the state and then you do something else. So I'd say it's almost the same, but you are right. Most people think of embedding or encoding information not so much as like a static beginning state preparation routine, but they think of it as actually a circuit. So there's these embedding circuits, and you can even train them and so on and so forth. Yeah, so there's no conceptual difference.
Great. And yeah, I guess one question was repeated, and I think is a good one, is what with a noisy quantum computer, the longer you run it, the more the information the more noisy it gets. So to what extent is this a limitation? What can we do about it?
Yeah, so we can't correct this noise. So we cannot, we know that, this is like the general story about quantum computing. We need to really avoid this noise and the corruption in the results. We need error correction. Error correction for all theoretically we know needs a lot of qubits to basically build a logical qubit with which is then error corrected. And so at the moment, the numbers of qubits we have are not enough. But there are a lot of mitigation strategies. So this is not like a field where I'm like working a lot in, but I love a couple of proposals. For example, you can, in a variation circuit, you can change your parameters, run your computation with different parameters, and they can, for example, extrapolate the result and, in this sense, like mitigate errors or like reduce errors or guess what's kind of how much your error, what error you're actually dealing with. So this is like kind of the research future which we're looking for. It's like error mitigation. There's a lot of ideas. At some stage, it won't be enough because errors start accumulating really quickly.
Yeah, I wonder, can I add one thing about the fault tolerance, which is the reason why you don't see it today is if someone has a 50 qubit quantum computer, they want to use it to push the limits of what you can do with 50 qubits. And you could use it maybe to simulate 2 logical qubits, but that would somehow not push the envelope as much as doing some new machine learning model. So we're capable of doing the building blocks of fault tolerant quantum computing. It's just, it's
Yeah,
not a
like
short-term
1 qubit.
thing. Yeah, or
You
one
can
qubit,
encode
yes.
Your entire,
Right.
your entire in this data set into 1 qubit. And then
Right. So just a little bit of time left. And I guess one question related to cost is that these things do require a lot of shots, as you mentioned, to extract the gradient. Maybe there are more runs needed than because of the measurement problem. You can use things like importance sampling, but still it's more costly. So, can you meaningfully comment on is this going to be very costly, or are the prices kind of very in flux right now? And it's hard to say what the costs will be like in the long run.
yeah, no, that's obviously whatever the companies fix, and this is more a business question. What will, as long as they think they still need to get early adopters on, and they still need to get people engaged, it will be cheap. And the moment there's enough interest to make a business case, I think it will be more expensive. Yeah, but the point is also maybe with the shots, maybe from a theoretical side, if this interests people, it's actually quite it's an interesting thing in these deterministic versions where you always estimate a value and you need lots of shots to get the statistics. So you estimate the value really with high accuracy. And these shots in algorithms often nip you in the butt. You often think, oh, I can show this nice little quantum speed up, maybe a quadratic one or something. And then all of a sudden you realize just by estimating things, and you need a bit of probability theory then to reason about this, all of a sudden I have the same scaling. So in the audience, I think Jonas, if you're there, he always loves to do this and tell you after a long idea that you had is this estimation actually pulls all the speed up. So it's a very important one, which I often forget mentioning, because for me a run is just a run, but a run needs lots of shots, and this is actually not trivial.
Right. So we might be ready for our break now, right?
Cool.
So
and
I think
if you stay on, if you've got questions about the notebook, I'll try to answer them. But yeah.
Great. So we have a 15-minute break and reconvene depending on your time zone at 25 minutes after the hour.
So welcome back from the break. We have the last video on this kind of topic of quantum machine learning now. It will be a little bit more theoretical, still on a high level, but it will talk a lot about kernel methods. So I enjoy this. This is now not so much an introduction anymore, but it's an example of a research field where people have found connections between classical and quantum machine learning that we can use to reason about quantum machine learning. And then after that, in a short Q&A, we will go to a slightly different angle that Juan will present, and I'm looking very much forward to that. So enjoy the video now. Welcome to the fourth part of the NeurIPS 2021 tutorial on machine learning with quantum computers. So far you should have seen that quantum computers are in some sense samplers of bit strings from interesting probability distributions or distributions we can generate in a very interesting algorithmic fashion. And you should have also learned that these generative algorithms we can just interpret very generically as a generative model. We can parameterize them, we can train them, and we can also encode data into quantum algorithms and quantum states. And then we interpret some stochastic property of the samples as some kind of prediction or output, and then we get deterministic models that replace neural networks and are quantum versions of machine learning models for supervised learning. And so in this part, we want to now ask, or go back to theory and ask, what are these quantum models? And it turns out, and this is something that's new, it only has been really linked in the last couple of years. It turns out that these second types of models, these quantum neural networks for supervised learning, that they have very elegant and very clear links to kernel methods. So we can say that there are actually, or a lot of them are actually just kernel methods that map data into high-dimensional spaces defined by these quantum states. And measurements on our quantum system are basically just defining linear decision boundaries in these spaces. And you can imagine that this link has a lot of consequences because it really connects quantum machine learning in some sense to a very, very important classical model that we know a lot about and that we use to actually gain an understanding to machine learning since decades. So the learning goals here is I want to show you this link. There's only very little math involved, and then you will see it's actually quite an elegant connection. And so this is the main part of the section, but I would also like to give you a bit of a glance or a feeling for how the quantum kernels of circuits, of algorithms that we look at the moment quite a lot, these variational algorithms. So what kernels do they actually make up? And this is, a research field that still has a lot of open questions. And then finally, I want to kind of conclude a bit of a cycle and get back to something that I spoke about in the very, very first introductory lecture, I want to show you an example how we can use this link to kernel methods, or how people have used it, to construct a quantum advantage proof for learning for a very specific case. So it's one of these rather artificial, but very, very artfully constructed proofs, where we can really say there is a setting in which quantum computers can be better for learning. So now I know you're dreading kind of this like introduction into kernel methods, and I won't actually do this to you. I won't go like into like what is a support vector machine and so on and so forth. I think that many of you know a lot of the basics of kernel methods already, and I won't be able to explain them if you don't. However, I want to spend a couple of minutes on giving you the important bits that we need to know from kernel methods, and these are the ones that I will then translate into the quantum situation. And so when I talk about kernel methods, you can always think of them as like generalized support vector machines. So for me, they're always like models where we map data with a feature map into a high dimensional space. This is some kind of feature space. And so the model is defined as an inner product between a feature vector, so a map data point, and some other vector from this feature space that we usually like identify as some weight vector that in linear models is often this like trainable weight vector. And as most of you know, like the idea of kernel methods, or the theory of kernel methods, has given us a lot of tools that say we only need inner products of these feature vectors or these data points in feature space to do everything that we're interested in machine learning, training, prediction, and so on and so forth. And so these inner products are called kernels. And for those of you who don't use kernel methods very often, whenever you see this inner product, just think of it as a comparison of a data point and another data point. And so this definition that I'm using here is basically a definition of a very generalized definition of a support vector machine that you find in this wonderful textbook by Steinwart and Christman that I can very much recommend and love very much. So again, like maybe a bit zoomed out, you have seen this picture a lot. Like, so this feature map, in some sense, the role of this feature map, and there's nothing different in the quantum case, is that we try to like map data into a space, and so that the feature map itself separates the data. So something nonlinear, something interesting is going on. And afterwards, in this feature space, we have a very simple problem. And so I'm saying this because if we now turn everything into quantum feature maps, quantum kernels, basically the goal of quantum machine learning, you will see very much shifts from like finding a model that does everything well to finding a model where the feature map works well. And so we don't know much about this part, but at least it limits the entire problem of quantum machine learning to something that we can actually pinpoint much better. Okay, 3 things you need to know from kernel theory that might not be so super obvious. So you might have heard of these reproducing kernel Hilbert spaces. What this basically means is that we can describe the space or the class of functions that these linear models in high dimensional spaces express. So we can basically rewrite them as a sum, like as a linear combination of kind of kernels in the input with other data points that are from our data domain. So this basically means like, any model can be written as you compare your input with any other point and you weigh this, and this is basically a function. Maybe a little bit more important, the models that we minimize, so basically the solutions to these empirical risk minimization problems, so basically your solutions to training, your trained models, they are from actually an even smaller function class. You can show that we have the same kind of linear combination of kernels, so you compare with data, but this time you don't necessarily need all the data from your domain to construct this function, but these solutions can be guaranteed or are guaranteed to be constructed from comparisons of the inputs with training points. And what does that mean? You know that the class of solutions for your training problems will always be a linear combination of m terms if m is the number of training data you have. And so this is like obviously interesting because instead of training like the weight vector in these high dimensional spaces, we can only train these like coefficients, these m coefficients. The picture that you see here, I hope this helps and doesn't confuse. So it's actually, I find it a nice visualization of like how these model functions could look like. So if you consider, like a scalar valued data, and then you say like your data sets are all these points on, the axis here. So now you kind of like plot this little inner product, like this kernel function. You fix the kernel in one of the entries and you fix it in one of the training data points, and then you just like vary the other one. And now you plot a lot of them. And so now what basically the second point is saying that trained models can always be expressed as these like, you can always like think of them as density functionals, but basically as these models constructed from the basic kernel functions. Now we also need like a little recap. So remember like the models that we are now actually limiting our analysis to, because we've spoken about a few in the last sections. So the idea is, okay, so quantum computers interpret it as samplers, give you like samples of bit strings, and you can compute some kind of like desired outcome, some kind of like a prediction, some value of your statistics that you consider as a prediction. And then I told you also that we cannot really like describe algorithms on the level of probabilities, but we need this deeper level of math, that's the quantum state vector. And so what we're looking here is quantum state vectors that have been generated by algorithms, where we first, as a part of the algorithm, we encode data, and this is quite separate now in this case, so this is important. And afterwards, we can do something else. We can, for example, like implement a trainable algorithm. And so then like kind of the distributions that we sample from depend on the data and the, trainable parameters, for example. And this is just another way, you remember like how I kind of like tried to put this into like a picture of what's going on like in the circuit. So the circuit diagram is what quantum computing people love seeing. But I now want to talk more about this like mathematical description. So I told you that most of the properties we're interested, so most of the predictions of models we can describe as a vector matrix vector product. And so the matrices are somehow like this unitary evolution, so the transitions of your state vector, and then there's one big matrix in the middle that gives us information on what we measure, and this is often like a simple measurement in most of the cases in quantum computing we're interested in. So this is our model, it's basically a vector matrix is vector multiplication. Okay, cool. Now we've got everything in a few steps only to actually show you why quantum models are linear models in some kind of space. And we will get to what the space is like in a second. So if you now take this model and stay with this picture math here, so there's like big vector matrix vector multiplication. This is a scalar in the end. And if it's a scalar, you can actually take the trace of the scalar. So the trace is usually something you do with matrices. This means you like sum over the diagonal of a matrix. But in this case, if you take the trace of a scalar, it's just the scalar itself. So I haven't changed anything. However, I gain a bit of freedom mathematically. And some of you might know that the trace is something that has a cyclic property. So I can kind of like shift vectors and matrices from the end to the beginning without like changing the outcome. And this is exactly what I do here. So I shift this like green block from the right to the left. So just a mathematical manipulation. And then I kind of conceptually relabel the first part as something that I call rho of x. And if you do the maths, so it's a complex column vector times a complex row vector, you get a complex matrix out of this. And this matrix depends on your input. And then I do the same thing with the last part. I kind of summarize like, my blue blocks and my measurement block into like something that I would just consider a new measurement, and this measurement is trainable. You remember, we can always conceptually shift from circuits to measurements. We can absorb circuits into measurements and create more complex measurements. So this is what's happening here, basically. And so what we get is this. This is exactly what we've been talking about all along, but we just use different maths. For quantum theorists, this kind of math is almost a little bit more familiar than even the other one, the vector matrix vector multiplication, because what it basically is, it's the expression of a quantum expectation value, so like kind of the description of stochastic properties of like samples from a quantum computer, but using a different formulation. So not using quantum state vectors, but in this case using density matrices. Some of you might have heard of this before. The density matrix formulation is completely equivalent to the state and vector formulation, but it is a little bit more powerful. So you can we won't do it here, but you can quite elegantly add classical dynamics and classical statistics to your expressions here. But so for now, what we use this is the following. This expression here that you see is nothing other than a linear model. So you map your data to a feature space, and then you take like inner products to other vectors in this feature space, if you consider the feature space of complex valued matrices. So basically, this is nothing else than a very special inner product. So trace can be considered to be the Hilbert-Schmidt inner product in like the space of complex valued matrices. So we have nothing else than a linear model in a high-dimensional space. And what does that mean? It means that our quantum model is a kernel method. And so now the next thing to do is to define the kernel, because in kernel methods we only need that and can construct everything out of the kernel, as I just said. And so how you construct the kernel is also quite simple. You take the same inner product, and now you take like kind of like one of these feature feature vectors, feature states, and another one of another input. And so this is like, in some sense, like now what we will call our quantum kernel. And if this confuses you, it's in some sense also, again, just a comparison of data points. So you map your data into this like quantum space of quantum states, but not the vector one, but the matrix one. So we had to do a little bit of a shift. And this was something, so if you see the two papers at the bottom, so the one like from us that come out a little bit earlier, we haven't, we were still in the state formulation, and there was always a square factor that was a bit annoying. And then in the second paper, you see like, okay, this density matrix formulation like basically like clears this up. And so you can think of it as like mapping data to these quantum states and then comparing these quantum states. So basically taking the trace of two quantum states. There are lots of ways of how to compare quantum states and define distances between them. This is maybe not the most typical one in quantum mechanics, but it is definitely one of them, and you can always think of it like that. So now, what basically happened here is that we now reinterpreted our quantum algorithm as one that maps data into like this feature space, whatever this is, this complex valued matrix feature space. And conceptually, what happens is that the measurement takes on the role of this weight vector in a linear model. So in some sense, you can, now interpret like these types of quantum models as just learning a measurement in this space of quantum states. I want to give you an example. This example might either confuse you or it might help you. If it confuses you, just like ignore it. And in this example, I basically just took Penny Lane. I implemented a specific quantum circuit, but only on one qubit, so a very, very simple one. So you see the quantum circuit on top. I encoded an input, and I'll consider here just scalar inputs, like just the real line. So I took an X, I threw it into our X rotation gate. So this is my encoding procedure. And then afterwards, my variation circuit procedure, so the trainable part, I used something that's called like a general rotation. It's defined by 3 degrees of freedom. And this is just the most general thing I can do with a qubit. So basically this purple part means do anything that you want if you just like specify the parameters right. And so this visual representation is a bit of a two-sided sword, because I haven't really introduced like this visual interpretation of qubits at the moment. So this is why it could confuse you a little bit. But I try just to motivate it in saying that if you think of a quantum state describing a single qubit, you have a quantum state of 2 entries, right? 2 amplitudes, one corresponding to the observation of 0 for this qubit, another one of 1. And these 2 entries are complex valued numbers. So you need 4 numbers in total, 4 real valued numbers in total to describe the qubit. But we can't plot in 4 dimensions. So we know that actually these state vectors are normalized. There's some kind of normalization condition, which means you only need 3 degrees of freedom. And 3 degrees of freedom, you can kind of like plot in 3 dimensions nicely. And this normalization condition gives you like then a sphere in the end. So this is just a quick explanation of what you see. But then what I did, I kind of like just took some training data, and then I visualized kind of how you map this training data to a quantum state in this representation that we can visualize. And you can actually see, in this case, our feature map is really simple, right? It even keeps like distances more or less intact, more or less, I'm saying. And then the rotation basically just rotates all my data. It doesn't change distance anymore, like something like very simple is happening there. And this is actually quite typical for this kind of quantum algorithm. And then the last little like ball that you see there, what I did, I kind of like made like a contour plot where I took every point on the sphere, which corresponds to any state I could get, and tell you what a measurement, so the so-called Pauli Z measurement, remember this was a measurement where I just asked, is the qubit in state 0 or 1, only that I rename it to -1 and 1, so it's just a rescaled probability of a qubit measurement. So I take this measurement and I ask for every state, what would the outcome of this measurement be? So what would my prediction be? So what you see in white is the region of the decision boundary. And I think this plot really shows quite nicely that you embed data into this state of quantum states, and then you kind of like cut through it in a linear decision boundary. So this is really what's going on here. And I also gave you, like, I wrote down the, the analytical expression of the function of the model that actually comes out of it for 2 reasons. First, I want to show you that, this whole quantum craziness basically still in the end gives you a function, right? This function might be difficult to simulate classically, but it still gives you a function. And in some cases, it's a really, really simple function. Actually, in many, many cases, it's a really simple function. And secondly, I want you to see that actually these functions very typically, at least for the circuits that we currently consider, maybe we should consider different ones, but these are the ones we're used to. They very, very generically like consist of building blocks of like sine and cosine functions. So they always have this trigonometric or like Fourier structure. Okay, now let's just apply basically all the results from kernel theory, or at least the three that we highlighted before. But you will notice that if we can now understand quantum models as just kernel methods, then all the results that people have collected in the last like 30 years or so will just apply to our models as well. So first of all, we have an alternative description of quantum models where we do not need to necessarily like do like unitary transformations in some Hilbert space. So the entire circuit part, the entire variational part is actually gone. We only need the kernel. We can also say that we know how the solutions of our problem look like. And so the solutions of our problem are just like, finite or like very small size, the size is the size of the data set, very small size linear combinations of these kernels. And I have to add also that these kernels, I haven't said this yet, but there's a very simple algorithm and recipe how to evaluate them on a quantum computer. So we can do this very easily already with near-term quantum computers. And so now I also like change the third point where I said like instead of training the vector, the weight vector, in this case, I say instead of training the measurement of the linear model, we can actually train just these parameters. So this switches the variational paradigm really to like this kernel-based training paradigm. And now I added again the picture from before, but now you probably asked like, okay, a quantum kernel is probably nothing Gaussian. So what is it actually? And I get back to this later. I just want to give you two very big consequences of this link. The first one is that if we can actually rewrite quantum models as like something classical plus a quantum kernel, then all what we're looking for in terms of like quantum advantages will be contained in this quantum kernel. And if this interests you, I want to recommend this paper that I'm showing there, where the authors construct kind of like a measure of like, or kind of like a diagram that you can follow to see if your quantum kernel actually is classically intractable or not, by comparing classical and quantum kernels. So this is like changed a bit the idea of how we also like interpret quantum advantages. And the second consequence is what I mentioned before, is that we really can shift from this variational training where, if you think about it, like what we do with the measurement is we parameterize it, and then the parameterized measurement gives us a subspace of the space of all measurements. And then we try to find like kind of the best measurement in the subspace. And this is usually a non-convex optimization problem. We can shift to a convex optimization problem. And even with this problem that kernel methods often have, that they have to like compute the pairwise, kernel or distance function of data points. Even with that, we see that in lots of applications, like on the small scale that we're analyzing today, this kernel-based training is actually faster and scales better in these regimes than the variational training for quantum circuits. Okay, so how do quantum kernels look like now? So I kind of like in these plots like use an input that's not one-dimensional anymore, but two-dimensional. What I did here is I just plotted like some of very typical embedding strategies. So these circuits, these green circuits S of X that we had. So people have like used a couple of them for a long time. And some of them like encode continuous data, but for example, the first one encodes actually binary data. So this looks a bit sparse, this plot. But you see there's something that is like very much Fourier-like. And this reminds you maybe of this like model structure that I was pointing out earlier. So these are like very typical ones that people have used. Recently, there has been this proposal of repeating kind of structure. So what I did, I took now the last one, and this corresponds to a circuit, and the circuit is now just repeated more and more times. And you see these like kind of like Fourier structures and these values and become more and more complex. So something is going on that looks very much like a Fourier structure. And it turns out that actually we can write down quantum kernels as a generalized Fourier series, like which is corresponds to a Fourier transform for functions that are periodic. So what you basically, if you're not familiar with Fourier series anymore so much, like just think of it as a Fourier transform, which most of you might know. And the point is, so any function can be written like that, but the point is that we have a very clear understanding of the frequencies. So depending on your embedding strategy, what are the frequencies that we see here? So if you give me basically frequencies you want to see in a kernel, I can almost like very precisely engineer these frequencies by just choosing the right gates to embed my data. And I also have a bit of an understanding of the coefficients of these frequencies, so how much they're weighted in these plots. This link is a lot harder and a lot more complicated, like mathematically, to really model. But what we can say is if we train a quantum model, we can say that we train actually these Fourier coefficients. And so if you work in kernel methods, this should make you like very interested, because in kernel methods, we often like think of the Fourier representation of kernels. And we know quite a lot of these spectral representation, and there are these ideas of spectral kernel learning and so on and so forth. So this is a very, very interesting connection here. So then lastly, let's get back to this like idea, or like this point that I was making, that we can use these kernel methods now to do what we set out at the beginning, and what I kind of discouraged you a bit in doing, which is to construct a quantum advantage for machine learning problems. And so I'll follow here like a very nice paper from you, Arunashalam and Kistan Temme, from like when was that? 2020, I guess. And so now a very clear recipe actually emerges. So take, for example, a problem that a quantum computer can solve well. And so they took the discrete logarithm problem, which is some kind of like a generalization of like a problem of applying a logarithm to a value. And then turn this discrete logarithm problem into like a concept class, so into a machine learning problem, basically, so that we have like a classification problem that comes out of it. And the third step is now, and this is where the kernel methods come in, if you can construct a quantum feature map, then in some sense, like, it separates the data. So what you see on the right would be like something like our original input space. On the left, you would see the input space after applying this discrete logarithm problem quantum algorithm. You can separate the data in feature space. And if on top of that, you can also say that the margins with which they are separated are large enough, which in this case, the authors can do, and which is like one of the really strong points of this proposal, you can actually talk about generalization of these quantum kernel methods quite nicely. So this is an example of a very artificial, but extremely beautiful end-to-end proof that quantum machine learning, there are situations where quantum machine learning is in some sense superior to classical machine learning. And this is like based on the idea of these quantum kernel methods. Okay, so this was a lot, but let's recap. So everything I want you to take away is that a lot of the quantum circuits that we analyze as models at the moment and that we train can be interpreted as kernel methods. This connects us to a whole lot of theory that we only start to exploit. And it also reduces like this quest for like, where's the quantum advantage? And this is only, I have to say, like something that we really start analyzing properly. So the idea of what are actually interesting kernels, not only ones that are better than quantum classical in some sense, but really interesting ones. This is still like a very much wide open problem.
Hi, welcome back. So we have a few questions left on the record chat. It might be that some of the earlier questions we just oversaw. So like if you asked questions before, which we didn't answer yet, please feel free to restate them. To start with one question is if Pauli X rotations helps with learning Fourier series, are there other gates which are specific to different tasks? Can you define quantum gates that help speed up learning?
Yes, so this is very close to what I'm preaching since a year in every conference and every talk that I go to the quantum computing community or the quantum machine learning community is we're using these Pauli X rotations everywhere. You see them in literally every paper. This is the workhorse. And that's the kind of slightly embarrassing part. It's not the workhorse because they're good for machine learning, right? Everyone has ever said they're good for machine learning. And this Fourier representation is more a observation, like that we see, oh, okay, something's going on here that we can describe with Fourier series. And they come basically from the fact that this is what the hardware gives us. So we can also not be too choosy, right? If we have really complicated gates, but the hardware cannot implement them, then at the moment we can't really experiment. So there's also reasons for this. But I think it's time now to ask, what are the building blocks? So I used to formulate this as what is the perceptron of quantum machine learning? And I'm not saying about what is a nonlinear activation function in quantum computing, but I'm saying what is actually the model that's a building block that's theoretically understandable, that's trainable, where we can do simulations, where we can prove learning results for quantum computing. And so I think this filling these black boxes of encoding, filling these black boxes of what circuits do we actually use, this is like overdue to make this step and to do this systematically. And there are lots of angles with which you can do this. So I think this is really the research question that has to happen soon. There's already obviously papers on that, but I think it's not big enough yet.
Sorry, that just came to another questions. One says, can we say that quantum models equals support vector machines supporting super fast Fourier transformations?
That's actually a super interesting idea. Super fast, I don't even know if they're super fast. So yeah, I mean, let's put it like that. If you construct your embedding with these Rx and Ry rotations that we had, so these poly rotations, how we do it at the moment, what you do, you have a model, as you say, the kernel is, this type of Fourier series, high-dimensional Fourier series. The models that you get out will also be somehow have to do with Fourier series. And training, you can also interpret as learning Fourier coefficients. I personally think this is important for theory. I think we can now use, for example, in kernel theory, as many of you might know, there's beautiful representation, like Fourier spectral representations of kernels. And we can now, for example, so I had a student who did something really beautifully, just like asked, okay, we know the spectrum of a quantum kernel and we know the spectrum of a Gaussian kernel. Can we not match them? Can we not like analytically say these are the gates to use so that we reproduce a Gaussian kernel? This has nothing to do with speedups. We just want to understand it. So I think this theory is beautiful to step away from speedups and just understand what's going on. In the longer term, I do not think we have a lot of advantage for learning Fourier stuff. But if I was a student and I had a year or two and would like to look into an application, I would definitely take this theory and then look into signal processing, for example. Actually, there's also a field called quantum signal processing, which is another super interesting connection. But so whether there are applications with this is actually unclear yet. So, very nice question.
Then the next question would be if the quantum machine learning seems to be advantage to SVM type models, what can we say about neural networks with quantum gates?
Yeah, so this is big debate. So also, like, I have to clarify that quantum computing or these quantum models are now not necessarily advantageous. So again, take off your advantage hat and just think of the theory. What does the theory give us? And whether like something is better for something else is a different question. We just know that we have an alternative now to the variational training paradigm that looks a bit like neural networks. We can also do the SVM route, and the theory is a lot more elegant. Yeah. So whether there's an advantage depends on if your quantum kernel shows an advantage. And this is still, we know there are quantum kernels that have the advantage, as in the example, but useful quantum kernels with an advantage, that's the open question. Anyhow, so how this like works now with neural networks. So I think so some people now try to, like in classical machine learning, kernel theory obviously is used to understand deep neural networks. And so there are links via neural tangent kernels and so on and so forth. And people are trying to like look into these links as well. So quantum neural networks, going to neural networks, going like making the bridge to kernel methods, which has a bridge to quantum kernel methods. I personally find this is not very clear. I think there are two separate paradigms. And the quantum kernel paradigm is also not explaining everything. So for example, it gets very complicated if you mix your trainable circuit and your embedding gates. So then the theory is not as smooth anymore. So for me, this is just a tool for theoretical understanding that's surprisingly general. If that makes sense. And then maybe because I mentioned it, so someone asked about are there other examples of classically intractable kernels? And I think one of the first ones, so what you can always do is you just take your favorite circuit for which you cannot draw samples or like simulate it classically. It's a little bit more tricky because you see in a kernel, the circuit is applied in a specific fashion. So you kind of like have an inner product of two kernels, of two circuits somehow. So you have to be a bit more careful about your intractability results, definitely. But so one of the first ones used a so-called IQP circuits. So that's a class of circuits where we also know quite a lot about, that they're hard to simulate. But I think it's more blueprint. So you give me a quantum algorithm, I can build your kernel out of this because the quantum algorithm separates data, it solves a problem. And then in the space of the solution, my problem is easy to do machine learning with. So I think the blueprint you can almost like churn out now. You can turn almost I'm claiming this, but you can turn out almost a lot of quantum computing results into kernels and just say there's an advantage. But it's obviously not as easy as that, because you want to have an interesting machine learning problem, and very often they're very pathological problems that they solve.
Okay, thanks. Then there was another question. Is it correct to say that feature space dimension is finite and completely determined by the number of qubits in the circuit?
Yes, exactly, very precisely. And I mean, the feature space dimension, if we consider this, obviously, like, one kernel can have lots of feature space. So you could probably take a quantum kernel, construct lots of feature spaces, maybe even infinite ones, but the one that we usually do the maths in is finite. There are quantum computers. So, for example, the photonic devices we're looking into at Xanadu, just to give you an example, that work in infinite dimensional Hilbert spaces, and they have very interesting properties. So, like, photonics in quantum computing has very interesting properties in terms of kernels. For example, you can very automatically implement a Gaussian kernel on a photonic device. You don't even have to do complicated things. But whether they are more useful, like, we haven't been able to ever show this.
So more kernel questions. What are the essential ingredients for getting a quantum kernel that is classically impossible to compute?
Yeah, so I think that was kind of the thing that I said. You're just like, you turn your algorithm into, you turn your quantum computing algorithm that you know is difficult to simulate into, actually, it's a little bit more complicated. So if you really want to have the proof, as I said, you first have to, like, show that there's you have to turn your quantum computational algorithm or the problem it solves into a learning problem, so some hypothesis classes. Then you have to show that the quantum computer can learn this. And then you have to show that there's generalization, so which usually means the quantum computer separates data and feature space far enough. And usually, I think these are the ingredients you need.
So maybe time for a last question. Are quantum circuits more than a string of unitary transformations?
Good question. In our model that we usually use in the most simple circuit model, no, we think of it as a string of unitary transformations. There are obviously, you can go to have, define quantum circuits with so-called quantum channels, where you, like, use subsystems of big unitary transformations and stuff. So there's a lot of games you can play, but I think it's enough to think of them as unitary transformations.
Okay, so I think that's was the last question for the session. Do you want to introduce the next video before it starts?
Yes, exactly. So that's now we do a really big switch, and now Juan will handle the last part, and I'll just sit back and enjoy.
Thanks. Yeah. So next video is about the other way around, kind of like can we use machine learning, classical machine learning, to understand quantum systems? And so we'll go into it now. Thank you. Welcome to the NeurIPS 2021 tutorial on ML with quantum computers. This is part 5, what ML can do for quantum many-body physics. My name is Juan Felipe Carrasquilla Alvarez. Let me recap a little bit what you've seen already during this tutorial. So you have explored what the model of quantum computing is, explored the meaning of the quantum state and its differences with respect to a probability distribution, explored the noisy intermediate scale quantum devices and variational quantum algorithms, discussed quantum computers as a special type of samplers, explored the question of whether quantum computers can help machine learning tasks. And we now ask the question, can ML help quantum physics? And I'm going to start by recapping or reintroducing the idea of a quantum state. So a generic specification of a quantum state requires resources that grow exponentially large in the number of degrees of freedom n, because the quantum state is a complex valued vector with, say, 2 to the n components in the case of a qubit. This growth is very dramatic, such that today's best supercomputers can only solve the Schrödinger equation, which for our purposes can be recast as solving a very large eigenvalue problem exactly for only systems with up to 45 spin degrees of freedom, or 45 so-called spins. So yet technologically relevant problems in chemistry, condensed matter physics, quantum computing and so on are much larger than, say, 45 qubits, and of the order of the Avogadro number, 10 to the 23, that we've seen in chemistry courses and so on. And there's quantum computing, there's variational algorithms and exact formulations of these important problems in chemistry and condensed matter physics. But quantum computers still do not work, and so we're still trying to figure out how to do quantum computing. And so the question is, can classical algorithms still help us solve some of these problems? And the idea is that nature is typically less complex in the sense that the amount of information in quantum states realized in nature often contain less information than that maximum capacity, that exponential growth that I was explaining in the previous slide. And this is because these problems contain a lot of structure. And so we exploit the structure in the techniques that we use typically to study the systems. And I want to highlight two of them that are very powerful. So one of them is called Quantum Monte Carlo, where the idea is that we have a stochastic exploration of the most important regions of this gigantic state space using Markov chain Monte Carlo techniques of the exact same nature of those MCMC algorithms encountered in machine learning. The other important technique that I like to highlight is tensor networks, which exploit the fact that quantum states realized in nature have little entanglement. And I wanted to highlight that in machine learning, these models, these tensor networks, are often called tensor decompositions. And one of example that is relatively popular is the so-called tensor train. Both of these techniques have led to profound implications to our understanding of condensed matter systems and quantum many-body systems in general. Now we enter machine learning. Machine learning community, as you know, deals with equally highly structured problems arising in natural data sets. And the key insight that both quantum and a few people, including myself, had a few years ago was that both quantum problems and machine learning problems have a lot of shared structure and symmetry. And so meaning that we can use the same tools to tackle this problem. So both natural data sets and in quantum many-body physics. So what are these commonalities, and are they important beyond mere resemblance? And so the first one that I'd like to highlight is the common mathematical objects. So for instance, in statistical physics, we study the equilibrium properties of classical statistical mechanics through the study of the Boltzmann distribution given by this expression here, P of energy equals to the e to the minus energy divided by the temperature, where energy describes the interactions between the degrees of freedoms in the system. And the analogy, for instance, that I have here is with respect to generative modeling, with the idea is to assign probability distributions to naturally occurring data sets, such as like handwritten digits or images and so on. Whereas in Boltzmann and statistical mechanics, we would like to understand the probabilities assigned to the spin configurations or the configurations of a set of molecules in a system and so on. Beyond that, we have quantum wave functions, quantum states that are also equally that have the same or a similar structure, where we are assigning amplitudes or probability amplitudes to, say, configurations in a molecular system or in a system of spin degrees of freedom and so on. And the commonality, or one more commonality between these objects, is their high dimensionality. And so all these problems are, and what we do with this techniques and systems is we're interested in exploiting and understanding these high dimensional distributions or wave functions to make progress in our fields. Okay. The other important aspect that I would like to highlight is that both correlations and symmetries are very similar in quantum physics and in statistical mechanics, as well as in machine learning. For instance, one example that I find very appealing is critical correlations that appear both in natural language and natural images, but also music and flocks of animals. And so here, for instance, I have one example of paper in Physical Review Letters in 2013, where they study the thermodynamic properties of natural images, and they are found to to be described by easy models of the same type of that we study in statistical mechanics. And interestingly, these natural images seem to exhibit correlations that are similar to the correlations of the easy model at the critical point. And that's what I mean by critical correlations. And all those critical systems exhibit power law decay correlations. In the same sense that classical and quantum systems behave at a, say, critical point. And by critical point, I mean, for instance, if you think about water evaporating from a liquid, there's a critical point or a critical temperature in which the liquid goes from, in which water goes from a liquid state to a solid state, to a gas state. In addition, the symmetries, like for instance, translational, rotational, reflection, and other symmetries, even gauge symmetries, that simultaneously enrich our understanding of these physical systems, but also at the same time improve the sample complexity of machine learning algorithms when we exploit them to define our ML models. Okay, so I've given you a couple of arguments for why this may be a good idea, but are these expectations practical, right? Like, do they lead to something useful? And so I'm going to try to show you a couple of examples where we demonstrate or where we argue that this is the case. And so I'm going to be introducing the idea of neural networks as quantum states, and what they mean and how we use them. And I'm going to show you two examples. One of them is Hamiltonian driven. The other one is data driven learning. And the idea is that when we train these ML models, these neural networks, we have some gradient signal, and this gradient signal can come either from a data set, which is if you want, the closest thing in spirit to what machine learning people do, but also this gradient signal can come from a physical principle. And so this example here, Hamiltonian-driven learning, is that idea that we can have a physical law describing some physical system, and we can use that laws to train our neural network models. And so let me first go into the first example, which is Hamiltonian-driven learning, which is basically finding the so-called ground state of a many-body system. This, if you want, allows us to understand the low energy properties of these systems that are realized in nature when they're in equilibrium with the system. So let me explain what this problem looks like. So finding ground state. So and when we're asked to find a ground state, so we're given a problem Hamiltonian, and we're asked to approximate its ground state. So what is a Hamiltonian in quantum mechanics? It's a very large Hermitian matrix that describes the behavior of the physical system at the microscopic scale. But for all practical purposes, we can think of this as a very gigantic matrix that is very sparse and very structured, and describes the interactions between the particles in a system. And finding the ground state, which describes the equilibrium properties of the system at very low temperature, amounts to finding the Hamiltonian's lowest energy eigenvector and eigenvalue. Okay, so we have a giant matrix. We need to find one eigenstate of the matrix, which corresponds to the eigenvalue with the lowest energy. Okay, so here on the right, we have a schematic representation of a Hamiltonian with only 5 particles. So as you can see, these Hamiltonians, these matrices are very large. And typically, as you increase the number of particles in the system, the size of this matrix grows exponentially fast. So solving this problem is difficult. And there are several approaches. You may try to solve the problem analytically, which rarely works. Or you can propose an ansatz. For instance, one inspired by machine learning techniques, such as a neural network, and then you try to rephrase the problem as an optimization. Okay, in modern variational quantum algorithms, this problem is this task is called variational quantum eigensolver algorithm, and this ansatz, instead of being a neural network, is a circuit parameterized with some numbers. Okay, so let me tell you a bit more about this problem. So about the problem in general. So Hamiltonians are very large. I said that already, and so the problem is computationally difficult, but they're very sparse. So meaning that the number of non-zero elements is not too bad. is doesn't grow so crazy. They're very structured and they have a lot of symmetries, some of which are common to important symmetries and inductive biases in machine learning. I'd like to highlight that the rows and columns indices of this gigantic are usually related to real space configurations of the particles, like associated, for instance, with having 2 particles at site I and 2 at site j, and so on and so forth. And they're typically ordered using bit string representations, okay? Such as very similar to the ones that were described in Maria's part of the tutorial. So what do we mean by finding the ground state using a neural network? So this is, I guess, a key slide that I like to spend a few minutes on. And so recall that we represent a quantum state as a 2 to the n dimensional vector of complex entries. So here we have this vector represented as psi. It's a collection of complex numbers associated with some bit strings that, if you want, label the entries of the vector, and that are also associated with the measurement outcomes that you would see if you measure the quantum state, as Maria was explaining in the first parts of her tutorial. So we have this 2 to the n dimensional complex vector, but we want to ask the question, or one important question to ask is, what does it mean that we represent this quantum state, which has so much information, 2 to the n coefficients, as a neural network? And so what we do, and to achieve this neural network representation of the quantum state, is we basically construct a function, psi of theta, that takes input these bit strings, okay? And when we and then we basically evaluate this function on all those bit strings if we wanted the full representation of the wave function. And this function psi of theta is of course a neural network that takes inputs, these bit strings that I'm displaying here. And so here on the right, I have a schematic cartoon of neural network with 3 layers: an input layer that corresponds to this bit string, a hidden layer, and the outcome, which is just a number. It's a complex number. And so what we're doing here, and what I'm saying here, is that as a consequence of doing this, we go from an exponential amount of parameters to a representation in terms of a function expressed by a neural network with a few parameters that whose number we can choose. And so at the cost of constraining the type of functions we can represent, because in this 2 to the n dimensional complex vector, we can represent basically any function on that, or on any vector of that dimensionality. But what we're doing here is we're constraining the number of functions, or the types of functions that we can represent, by assuming that each entry can be represented by the same neural network. Okay, so that's the idea. That's how we're going to be approximating this huge vectors. We're going to be using neural networks. And let me tell you that this is not a new idea necessarily. So this has been attempted since the 90s, indeed during one of the AI winters in the 90s. And one of the important papers that came out of that of those studies is the artificial neural network methods in quantum mechanics by Lagares, Likes, and Foutiadis, where they studied solutions to the 2-dimensional Schrödinger equation. So it's a very easy, simple problem, but nevertheless, the idea was very interesting, very forward-looking at the time. And then what they checked is that they can solve this type of Hamiltonians or Schrödinger equations using neural networks. In that case, they use feed-forward neural networks at the time. There was another example, which is actually by myself and my colleague Roger Melko, where we studied a different Hamiltonian. It's called the so-called Kitaev's toric code, and we were able to rephrase finding the ground state of this particular Hamiltonian as a convolutional neural network, and where the input is again one of those binary configurations where, like, this binary means like blue is 1 and white is 0. It's just that this bit string configurations are are placed in a two-dimensional grid, and then we use the convolutional neural network to explore that bit string to assign a complex number to it, which we call psi here at the end, psi of sigma, where sigma is this bit string configuration. And perhaps the most important research article on this idea came also in 2017 in this paper by Giuseppe Carleo and Matthias Streuer in Science, where they checked that numerically optimizing this neural network wave function produces very accurate solutions to many-body problems to prototypical many-body problems in condensed matter physics. In that case, what they used a restricted Boltzmann machine neural network, and they explore, and this, out of this paper, a lot of people got excited about this idea and started exploring this in many different contexts, including obviously condensed matter physics, but also quantum chemistry, material science, atomic physics, high energy physics, field theory, and quantum information, nuclear physics, combinatorial optimization, and much more. So I don't have time to explain or to have perhaps a literature review about this explorations, but I invite you to check these three papers, one by myself in Advances of Physics, one by Giacomo Torlai, and on the archive, and this one by Giuseppe Carleo and Sirac, Cranmer, and collaborators, where they explore the whole idea of using machine learning in the physical sciences more broadly. So how is this numerical approach to solving many-body problems work? So let me explore that. So there's a numerical approach based on the idea of variational Monte Carlo. And what this variational Monte Carlo is just basically using Monte Carlo to optimize this neural networks understood as a quantum state. And so the ground state search, finding the lowest energy eigenstate of that gigantic Hamiltonian, is reframed as an optimization problem with an appropriate cost function derived from some physical principle. The physical principle that we use is the so-called variational theorem in quantum physics, which says that the expectation value of the energy of this Hamiltonian on that neural network representation of the wave function is greater or equal than their true eigenvalue E0, where E0 is, again, the lowest energy eigenvalue corresponding to the ground state of this Hamiltonian. So as I said, this is the psi theta is a neural network parameterization of the quantum state. And what I'm going to argue is that it is possible to compute E theta, this variational bound on the energy, using Monte Carlo simulations of the same flavor that people use in classical ML or in classical statistics. Not only that the energy can be computed, but also the gradients of the energy with respect to the parameters in the neural network. And one thing I would like to highlight is that there's no data involved in the solution here. So everything, or all the gradients and all the information about how you get those gradients comes from the Hamiltonian itself, from the problem. Okay, so this parameterization is, inputs as the spin configuration or this bit strings, output as the value of the wave function. Okay, so how to generalize the, neural networks to represent a quantum state? That's a good question. I'm going to introduce in the context of recurrent neural network wave functions, as introduced by my PhD student Mohamed Hibat Allah in this physical review research paper in 2020. So typically, so on the right, on A, we have a traditional recurrent neural network representing some probability distribution. And what we do is basically we take the square root of this distribution and construct a quantum state out of this probability distribution P of sigma. Okay, where sigma again corresponds to one of those bit strings that you've seen already a couple of times. Okay, and so it's this quantum state, as we say in quantum physics, it's a superposition of all those bit strings. Okay, so that we represent on our classical devices in terms of, in this case, a recurrent neural network. But quantum states are not a probability distribution; they're typically complex valued, as I was saying, right? It's a 2 to the n complex value vector, and so we have to add some phase to the probability distribution assigned to a bit string. And so what we do is we generalize the RNN and add a so-called a phase layer that produces some psi I, or psi 1, 2, 3, and so on. And out of those complex phases that we can get out of the hidden vector of the RNN, we basically construct a phase for each of these configurations. Okay, so on top of assigning, as in natural language processing, value of probabilities to some bit string or some words or phrases expressed as a bit string, we assign a complex phase. Okay, so that's the generalization. And then, so we have to train this model. So how do we do it? So as I said, I was arguing that this bound on the true energy of the system can be computed, as well as the gradients with respect to the parameters in the recurrent neural network through sampling. And the idea is that we write down this bound in terms of the square of the amplitudes expressed by the recurrent neural network. Okay, and so what we do is we interpret this amplitude square as a probability distribution. And what we do is we then can use Monte Carlo averaging to compute this expectation values for this average energy, if you want, as averages over the Hamiltonian in some sense. And so what we do is basically we take samples from the recurrent neural network squared, and you average this this quantity here, so-called the local energy, ELOC, okay? And the good news is this ELOC is easy to compute, okay? The gradients are expressed down here, and luckily they're also easy to compute via Monte Carlo averaging, okay? So this is the whole procedure. You take the wave function, the RNN, you sample, you compute the energy and the gradients, and you follow the direction of the steepest descent, as in any machine learning task that uses gradient descent techniques. And this is just to show you an example that demonstrates that the solutions that we found, so for, say, correlation functions and basically expectation values of some quantity, match very well with traditional techniques such as density matrix renormalization group, which have been developed for the past 30 years. And what we find is that these recurrent neural networks work equally well at describing the physics of the systems as expressed by these averages over the samples of the recurrent neural network. So that's, I'm just showing an example that we can be successful at using these techniques and problems that are relevant for for the systems we care about in quantum many-body physics and condensed matter. So this is a little bit of a hands-on tutorial, and what I'm going to be doing now is to show you how a code implementing these ideas that I explained looks like. But I encourage you to look at this tutorial by myself and my collaborator Giacomo Torlai, where we explain how to use neural networks in quantum many-body physics. We provide the paper, and as well as a bunch of code examples which are written in TensorFlow and other packages. But in particular, let's look at the main contents of this variational Monte Carlo for a Rydberg atom system now. So, as I said, this is written in TensorFlow. You don't need anything else, just Python and TensorFlow. And what you see here is just on green how we specify the geometry of the system. So here we have a two-dimensional lattice of say spin degrees of freedom or the states of a Rydberg atom, and so I use this up or down spin as my characterization of these bit strings that I was discussing that characterize both the Hamiltonian as well as the wave function. And so I'm going to say that down is equivalent to, say, 1, and up is equivalent to, say, 0. So we have a system of Lx by Ly, a number of spin degrees of freedom or spins or number of bits in the the wave function, and that's specified here in green in the code. And then we have the Hamiltonian that is defined in terms of these operators. The important thing is that they define this gigantic matrix, and this matrix takes some inputs, and the inputs are omega, delta, and V. And so that's specified here in orange. We specify V, omega, and delta. And then we specify the parameters of the RNN, which is the number of hidden states in the RNN here in orange, a seed for sampling the RNN, the number of epochs, the dimension of the input state of the RNN, which is 2, because we have ones and zeros at each call of the RNN cell. In red, we have the optimizer. In this case, it's going to be an Adam optimizer with a small learning rate. And then we basically define the architecture. In this case, we use Keras, gated recurrent units, with some initialization, regularization, and then a dense layer that computes the outcome of the RNN. So in this case, because of the structure of the Hamiltonian, we know that the ground state wave function is positive. There's no phases. This is due to a theorem by Perron and Frobenius. And so we ignore the phases of the wave function. So basically, this RNN looks exactly like an RNN that you would use for, say, topic modeling or for language modeling in natural language processing. Okay, so this is the construction of the RNN. It's just a simple Keras construction of a GRU. And then, so let me go ahead. So then we said, if we want to compute the energy or the variational bound on the energy, we need to take samples of the RNN, okay, which is this psi square here, and then average over the local energy. So let me first explore how to do the sampling. And so you may have seen this before, but when you sample an RNN, you just basically call the RNN cell. Once you compute this conditional probability, and then you sample the conditional, and then you pass the sample that you got to the RNN again, and you compute the conditional distribution on a P of sigma 2, condition on sigma 1, for instance. You sample it, and so on and so forth. So this is how you typically sample in recurrent neural networks in natural language processing. So this sampling loops is starting here in green. We do the forward pass. You use the RNN cell to compute this log probabilities, conditional probabilities in blue, and then we sample in red. We use a random categorical sampling out of this distribution, and then we collect these samples. Okay, we loop over this loop here in green, and at the end we return the samples that we got and the log probability assigned to those samples as seen by the RNN. Okay. Then we also need to compute this log of the amplitude of the RNN wave function, which is this function called log C. So given some samples, some collection of bit strings, we basically call the RNN, and this is done here in blue. And we call the RNN cell a bunch of times, and we compute the probabilities through the dense layer, and then we basically reduce the whole thing to compute the log probability or the log of the amplitude of the wave function, and then we return that's required to compute the energy, and then we have the local energy, which is, it has two pieces. It has one piece that's independent of the wave function, that where there's terms in the expression below cancel, so there's ratio of amplitudes of wave functions cancel, and there's so that depends on how the Hamiltonian looks like and so on. But then there's an off-diagonal part where computing this ratio is important, which is this line here in green, where we have some part of the Hamiltonian that contains these ratios, and then the ratio which we compute as the exponential of the difference of logs. Okay, so that's it. Then we have an optimization loop. And so it starts here in blue, the first thing we do is sample the RNN. So we use the sample function, and we ask to collect NS samples, and then we compute the log of amplitude of the wave function, the local energy, and as well as the A0, like the bound on the energy that we're trying to evaluate. And then we define some loss function that is such that if we take the gradient using TensorFlow automatic differentiation, we get the gradients that we're looking for. So I'd like to make connection with some of the techniques in machine learning. So this estimators of the gradients coincides with the reinforced algorithm, or the score function estimator, however you want to call it. Plus, what we do is we use some variance reduction that is equivalent to the so-called baseline that is very common in reinforcement learning. And then basically we take this loss function and compute the gradients, which again in turn coincide with the gradients that I was looking for using AD. And then we just basically optimize and so on and so forth until we reach some convergence, hopefully a solution close to the exact both lowest energy eigenstate and the energy close, hopefully, to the ground state energy of the system. So here I took a look at a small 4x4 system. So Lx and Ly is 4. We select some parameters in the Hamiltonian, V, omega, and delta, corresponding to this Hamiltonian I was trying to explain here on the right. And then we basically run this optimization loop. And what you see here is that in blue on the right, you see that the energy is a decreasing function of the optimization steps. And indeed, as we reach about 1,000 iterations, we hit energy bound that is really close to the exact one, which is known for a system such as on a small system, this problem can be solved using numerical diagonalization exactly. So what we see is that this RNN gets very, very close to the exact value. Of course, the solution could be improved by making the RNN more and more expressive and running further optimization steps. And that's it for this topic. So let me go on to the next example, which is the data-driven learning. So this one is the closest in spirit to machine learning tasks, and is the idea that we can reconstruct a quantum state out of measuring a quantum device in a real quantum experiment. Okay, so data-driven learning of quantum states, or the so-called idea of approximate quantum state tomography of large systems. So, and the idea is that we need to do this because standard quantum state tomography is very expensive. It's indeed exponentially expensive, but nevertheless, there's a lot of progress in controlling large quantum devices, such as quantum computers, cold atom experiments, trapped ions, and more. And there's a lot of availability of arbitrary measurements performed with great accuracy. The problem is this bottleneck of limiting the progress on estimating this large quantum states is the curse of dimensionality, which is, if you want, exactly the same as the one you would find in a traditional machine learning task. So these are examples of this device is growing really fast and really big. So 51 atom simulator, 53, 1,800 qubits, and so on. So this growth is really dramatic. So let me show you how to do this, right? Like how to take an experiment on a quantum device and transform it into an estimation problem of the quantum state. Okay, so in other words, how to collect these data sets, where these data sets is going to be associated with those bit strings that I was describing before, associated again with the quantum state. Okay, so the data set is going to look a little bit like this. Okay, so what is quantum state tomography? Exact or an approximate. So you prepare an unknown quantum state, you apply a measurement that probes hopefully enough information about the quantum state, and you so you may have heard that when you measure a quantum state, you destroy the state. So you basically end up with just a bit string of of data and a wrong quantum state, and so you have to prepare the state and measure it again. And so we repeat this measurement and this preparation and measurement of the quantum state multiple times until we collect this huge data set that hopefully represents the statistics associated with the quantum state. Okay, and so after that we use this data and we infer a reconstruction of the quantum state consistent with the measurement outcomes, consistent with the data. Okay, so that's the task of quantum state tomography. So let me give you a bit of a description of the collection of the data set and what's the statistics behind it and so on. So we use operators that describe the measurements, so that describe the experimental apparatus that collects the data. And there's a rule that connects quantum theory, namely the quantum state that you're producing, with the experimental apparatus you use to measure it and the statistics that you see in the experiment, right? Like the probability of observing some bit string A. And so this is described by some measurement operators, or the experiment is described by those operators. And if this experiment probes enough information, then we can, information about the quantum state, we can do a lot. So, and the idea is that you can think of this quantum state rho as an object, right? That you're looking from multiple directions, right? And so if this object, say, let's think of if this object was a three-dimensional object, we would need to look at it from different perspectives, right? And this is the analogy of choosing different measurement operators, right? Like that we need to look at the object from different directions for us to be able to, say, have a high fidelity reconstruction of what the object looks like, okay? And in those cases, if there's a lot of information about the state, if you look at it from different angles, what we say is that this measurement statistics contains all the information about the state, okay? And so we can use this data set collected out of this probability distribution to infer what the quantum state rho looks like, okay? And mathematically, we say that the relation between rho and the distribution can be inverted. So in here, we go from rho to P, but if you measure it and you have a lot of information about it, you can go from P to rho. And so this is the expression that you see here. Out of this probability distribution or samples from it, you can try to infer rho, okay? And so that's the idea. That's what we explored. And so how do we parameterize a quantum state and how we learn it, right? So that's the next question. So the insight was this, right? Like, so instead of parameterizing a rho, we parameterize this probability distribution, P, using a machine learning model. In this case, we used a recurrent neural network, but you can use any transformer, a GRU, or NAID, and so on. So, and the reasons we use those is because autoregressive models allow for exact sampling, and they have a tractable density, so that we can use, for instance, maximum likelihood estimation of the same type that is used in statistics and machine learning. And so ultimately, if we take that, we collect that data set that I was explaining before, and we train a probabilistic model P, then we can construct a model for the density matrix rho model, and then out of that infer a lot of things about the quantum state, okay? And so with that, let me show you one example, or two examples, where we've done measurement on a system with 50 spin degrees of freedom. And we've done this synthetically. We have not done this experimentally, but we've simulated the measurement on this system. And what we see here in red is expectation value over some operators, sigma x, as a function of where they are located in the system. And what we see is in orange, we see the synthetic data, and in green, we see the reconstruction of the RNN wave function of the RNN quantum state that we constructed. And likewise, we see in B that we can have some other two-body correlation functions or two-body expectation values, and what we see is, again, good agreement between the synthetic state and the reconstructed state of the RNN And then as a second example in C and D, it's the same. We constructed the ground state of a different Hamiltonian, in this case, a two-dimensional Hamiltonian, and we compared this expectation value of correlation functions for the synthetic state and the reconstructed state with the RNN. And so this just shows that this whole idea works relatively well. So with this, let me conclude. So I'd like to say that modern machine learning techniques have started to spread through the landscape of quantum matter and strongly correlated systems research. There are a lot of opportunities that machine learning techniques, ideas, and especially research culture can spark in the field of quantum physics. And that now it's a privileged time for machine learning and quantum systems research due to the enormous opportunities arising from both sides, machine learning, artificial intelligence, and quantum computing, which are, I think, in my opinion, are two of the most promising computing paradigms of the century. And with that, I'd like to thank you all for your attention.
So welcome to our last Q&A session, where we can ask questions of Juan about ML for physics instead of physics, ML for quantum instead of quantum for ML. And yeah, there's a few interesting questions in the chat. So one of them that appeared a feed times was why use RNNs instead of other architectures like a simple feed forward and neural network?
Yeah, so that's a great question. Thanks. So the main reason, so I mean, in principle, you can use any of these architectures, feed-forward neural networks, and so on. And this was the case at the beginning when people started exploring this idea. But then, so as I was trying to explain in the video, there's a sampling process that you have to carry out for you to compute, say, expectation value of Hamiltonians and operators in general. And there's so there's this sampling process, and so if the wave function that you are finding encodes a landscape that is rough, so this sampling process becomes very tricky. It becomes difficult because you're using Markov chain Monte Carlo, and this Markov chain sometimes can be very slow depending on the distributions encoded by the models. Whereas we used RNNs, which independently of the distribution that they encode, they can always be sampled exactly. Okay, and so basically you're guaranteed to get always, like, every single sample you get out of the RNN, it's an exact sample of the distribution that is encoded by the RNN. And so this translates into higher quality expectation values. So your energy is going to be more accurate, and as well as, like, more importantly, perhaps the gradients that you're trying to estimate as you improve the representation of the wave function that you're trying to capture. So I think that's the two main reasons. So the exact sampling, and I forgot one more, which is the tractability of computing the amplitude of the wave function. So if you use, for instance, a restricted Boltzmann machine or a feed-forward neural network as your representation, so these models do not, they're not normalized. So if you sum over all the input configurations squared, they do not sum up to 1 in general. So you have to compute the normalization of the wave function, which is a very computationally difficult problem in general. Whereas these RNN wave functions, the way we define them, they come already normalized. So given, for instance, 1-bit string, you can compute the amplitude of that wave function, and explicitly in polynomial time.
So I guess that's last one is an advantage even over tensor networks.
Yes,
right?
In tensor networks you have to normalize. And for instance, one thing that is particularly important is the fact that RNN wave functions can be defined in 2 dimensions or in 3 dimensions, and they retain this aspect. Whereas a 1-dimensional tensor network, matrix product state, or a tensor train, I mean, those are easy to normalize, and you can always compute this probability amplitude. Whereas when you extend them to 2D or 3D, then they become very difficult to contract and very difficult to normalize and to compute this probability amplitudes. And that, yeah, exactly, that's perhaps what you're mentioning. And there's one name in particular, it's called PEPS, projected entangled plaquette states, where this contraction is, I think, in the sharp p-hard complexity.
Yeah, I hadn't appreciated that benefit of these quantum neural networks.
Right.
So, yeah, one question was, if you want to optimize via back propagation, what form of how should the Hamiltonian be represented? Do you need a neural network representation? Is it enough to just have it in the normal physics way of some equalities?
Yeah, so that's a great question. So in general, so we don't, so for the whole procedure to work, so you just need a formula for the Hamiltonian. You don't need to write the Hamiltonian explicitly, it's too big. So all you need to know is, so given a configuration X, like one of these bit string configurations, all you need to know is what are the non-zero elements of the Hamiltonian that are connected to that configuration. And so for local Hamiltonians, this is typically a polynomial number of them. And so you don't need to write down the Hamiltonian in matrix form and so on. All you need to know is how the different elements connect to each other. And so you don't need like a neural network representation or an explicit matrix representation for the Hamiltonian for the procedure to work. And the backpropagation part comes in the calculation of the gradients. And when it comes to computing this gradients, the backpropagation works exactly the same as it works in machine learning. So the backprop is the same. Mm-hmm. I hope that was a bit clear, but
great. Yeah,
I can expand.
Oh, and I really like the last question. So, for tensor networks, I feel like we're all getting some intuition for what their strengths and limitations are in terms of what they can represent. But for the RNNs, yeah, what's some intuition for when they can represent something or when they can't?
Yeah, so this is a much harder question, but it's a great one, and it's, I think, currently being explored in the literature and so on. And the answer is I don't know yet. There's very little work on what people call inductive biases of these models with regards to what they can do for quantum physics. There are a couple of papers, though, one from Huitao Sheng at MIT, where he argued that they behave similarly to matrix product state, for instance, that these models, as they become more and more powerful, they are able to capture longer and longer correlations. But if you have a finite amount of parameters, what they do is they eventually decay exponentially, like correlation functions and mutual information, that they eventually decay exponentially. So this is exactly how matrix product state behave. And so it's basically telling us that this is the case, that they have a similar structure, and indeed they have this product structure of the chain rule that we use to construct it. And so they retain some of that product in the matrix product state. And so it's natural to expect that they behave somewhat similarly. But I think this question has not received the attention it deserves. It's very open.
Yeah, that makes it. So the differences between them and MPS in terms of representability are subtle then.
Yes, they're subtle, and there's not one-to-one translation between, at least between RNN and between MPS. And so ultimately, right. So the cool thing is RNNs are in the end universal function representation. So you hope that as you make them more and more powerful, they eventually going to be able to capture many ground states. But how you go from very few parameters to many and what happens in between, it's not clear yet.
Right. Yeah, that's pretty interesting. So one question was about, for people who want to get into this literature, where should they learn about what's a good condensed matter introduction? And maybe one answer would be a tensor, one of the reviews of tensor networks, right? But are there, for the NeurIPS audience, what would you recommend for an entry point into condensed matter, the condensed matter problems addressed here?
Yeah, so for the condensed matter, there are very there are reviews about machine learning tailored to condensed matter physics. So I think those are good entry points, since they use a language that people in machine learning would find familiar. And so there are several reviews that I can point out, and maybe I can point to some of them in the chat when we're done. And
great,
yeah.
Great. There was a question: would a bidirectional RNN be helpful?
Yeah, so that's a good question. So we've explored this idea, and the thing with this bidirectional RNNs is that they become symmetric with respect to mirror image. Okay, and so if your system encodes that particular symmetry, this mirror symmetry with respect to, say, the origin where you place your quantum system, then this bidirectional recurrent neural network is beneficial. It would just decrease the sample complexity of what you're trying to do. And so, yes, that's a good question, and indeed it helps.
Well, since I don't see another one, maybe I can give a little time. I can briefly ask one myself. One thing that people struggle with is to simulate gauge theories, like lattice QCD, and either for gauge theories or for general symmetries, is there a nice way of taking advantage of the symmetry and designing these quantum RNNs?
Yeah, so I'm not an expert on this, as I have not worked on it, but people have designed neural networks that respect gauge symmetry, and there are at least I know 2 or 3 papers, actually, yeah, 3 papers, and so there are, for instance, models for continuous gauge, models that are in the continuum that contain gauge symmetries. So this has done, I think, at MIT by Fiala Shanahan. And there's also 2 papers from Flatiron Institute where they have discrete degrees of freedom with gauge symmetry, and they have explored both restricted Boltzmann machine that encodes gauge symmetry, and also autoregressive models very similar to the ones that I described in my part of the tutorial that respect gauge symmetry. So I think there's progress along the way of encoding gauge symmetries and other symmetries as well.
Great, thanks. Well, I think it's time to move to the closing remarks. So awesome. Maria and Juan, I'll let you take it from here. Thanks everyone for all the questions.
Is Maria around? So maybe I can start with my own remarks. They're brief, but so yeah. So I think what I wanted to convey as a concluding remarks is that there are a lot of opportunities, both basically at the intersection between quantum computing, quantum many-body physics, machine learning. There's a lot of exciting avenues for research, and that we should exploit this and maybe perhaps bring the 2 communities together and explore these questions more broadly. There's ample opportunities both in quantum physics but also in quantum computing. There's a lot of interest and excitement, and yeah, that's kind of like what I wanted to say or convey, that there's a lot of opportunities, and we should exploit them. And I pass it on to Marie.
Great. I just had my laptop freeze twice during the last 5 minutes. So if you don't see me, then why don't you take over and just finish it off? the most important thing before they get cut off, thank you so much, Aaron. Thank you so much, Asha. Thank you, Mark and Mira from the background. Thank you, Slides Live team. Thanks all of you for listening. And what we'll just do in the last couple of minutes is to bombard you in the chat with links. If my computer holds out, I'll just start and try to comment on them a little bit. Some of them you've already seen. So a wonderful example, if you want to get involved into research and learn a bit more, is the QTMO conferences. So I'm talking now about machine learning with quantum computers. There are a lot of recorded talks there. Another introduction is an edX course by Peter Wittek. I posted this just now. Beautiful overview of parameterized circuits that I also have in the talks linked is this one here. And then what I haven't mentioned in the slides, because it's unfortunately behind a paywall, but we have a book, so me and a co-author, Francesco Piccione, on machine learning with quantum computers that touches a lot of those things. Unfortunately, yeah, it's from Springer, but if you can find my email address in papers and you send me an email, maybe we can make a plan so that you don't have to pay. Then we've got on quantum kernels, we have nice demos in software frameworks. I have to mention all of what I say and what I post is very biased. So you see a lot of also stuff from Penny Lane, but also from IBM. And then I'll link to the overview paper, almost done. I'll post again the software frameworks. Oh gosh, this is really bombarding you. And then lastly, and so this is, the quantum computing community, especially in software, is really big. There's a lot of events, there's a lot of hackathons. And so the best example is the IBM Qiskit community, because they've got really a lot of events and a lot of things where you can profile yourself. So I'll put a link there. And then the last one is really a bit of self-advertising. We have a really fun Q hack to the quantum hackathon coming up with a lot of quantum machine learning, which should be also easy accessible. I don't think I have to pay or something like that. And it should be a fun retro event. Yes, so on. Off to you if you want to add a couple of things.
I just I added my remarks during your little break. Yeah, so
lovely. Then, yeah, everyone, you're off. Thank you so much for listening and see you soon.